Good morning, everybody. Can you guys hear me in the back? All right. So let's get started with. Elsa, do we need something before we get started, or we ready? Okay. All right. So let's get started with the tutorial. Compute Express Link, which, as we all know, it's an open industry standard for composable computing. It's a small group here. Please move forward. Ask questions whenever you have. There are 4 of us here that we will walk through the material. There is a little wager going on here, friendly wager between us, who is going to stick to the 45-minute timeline and who is not going to stick to the 45-minute timeline. So just letting you guys know. We will have 15-minute break around 10 a.m. roughly, but if you need a break before that, just let us know. So with that, let's get rolling here. So this is the consortium, 250 plus member companies. You can read the board members' names out up there. Very successful as a consortium. We started in March of 2019 when we had the 1.0 spec. Then September 2019 we incorporated. We also did a 1.1 spec on behalf of the consortium. November of 2020 we released the 2.0 specification, and we'll talk about what came in each and every one of these specification release. And August of last year, just before FMS, we released the 3.0 specification.
Can you introduce yourself?
Oh, yes, minor details. Yeah, my name is Devendra Das Sarma, and we'll have each and every one of the speakers introduce themselves as they come up. Mahesh Wag will go after me. I work for Intel. I'm an Intel senior fellow, and I am also co-chair of the CXL board technical task force. I know that's a mouthful. So generally work in the area of IO technologies, PCI Express, CXL, UCIe, which is the tutorial that's coming up next, among other things. Thanks, Brian. I always forget to introduce myself because I feel like we know each other here. It's a friendly group of people.
Definitely happy to have you here. Thank you.
Sure. Agenda-wise, as I said, little friendly wager between us, roughly 45 minutes each, 5 minutes Q&A. I'll do the easiest part, introduction to CXL, and these guys will do all the heavy lifting. Mahesh will talk about protocols, memory pooling and sharing. Mahesh Natu, the other Mahesh, will talk about software and error management, and Vince will talk about fabric and fabric management, and also conclude. So here is the industry landscape today, right? I mean, we all know that there is the proliferation of cloud computing, AI, and analytics. There is a huge demand for compute and communications from there. Network and edge is getting, becoming more and more on the clouds. You want to do more processing over there. So all of these are causing an insatiable demand for compute. So once you have the insatiable demand for compute, not just homogeneous type of compute, but heterogeneous type of compute, right? So you're having people deploying everything that they can possibly to solve the types of problems they have. Whether it is CPUs, GPUs, FPGAs, purpose-built ASICs, right? Everything that you can think of, right? The problems are big enough that people are deploying solutions to solve that problem. So more of those demand means that we need more memory bandwidth, we need more memory capacity, you need to feed the beast, you need more IO bandwidth, right? So all of those things. So we are in this virtuous cycle of innovation, and that's the context in which CXL came into being. CXL started off as a breakthrough for effectively, and we'll talk a little bit more about that. We just wanted to build something on top of PCI Express infrastructure. There were 4 sets of industry challenges that CXL solves, and we'll talk about them. By the way, we have a tutorial if you're interested. It's an archive. You can it goes through a lot of the details of CXL. But basically, we said that build on PCI infrastructure, it's ubiquitous, so you can take advantage of the infrastructure, but fundamentally we overlaid coherency and memory protocol on top of PCI Express and delivered as an open industry standard. Now let's talk about that particular approach. So fundamentally, as I said, so PCI Express, if you look at the picture here, you have a host processor, direct connect model with an accelerator, and you have PCI Express, which is effectively the CXL.io. So it's the PCI Phi, all the CXL.io, everything is more or less PCI Express. We just leverage that infrastructure. On top of that, we multiplexed two other protocols. One is CXL.cas, which is for caching semantics, and the other one is CXL.mem for memory semantics. Okay. Why did we do that, right? So fundamentally, the challenges with this heterogeneous compute is effectively today the way in PCIe the model works is you have to move your entire data set between a CPU or a GPU, between GPU back to the CPU. So everything needs to move, right? So you carve out a certain task, you send out the entire data structure, let the accelerator work on that, and then sends it back to the CPU. So everything basically it's like a coarse-grained data movement model, right? A lot of these usages, they require more finer-grained data movement model where you want to treat the memory as a uniform space, right? And a couple of things that stand on the way is effectively, even though PCI Express is what we call a load store interconnect in the sense that you have direct memory access going across PCI Express, those accesses are all non-coherent in nature, right? So what it means is that devices cannot cache the system memory. If there is memory attached to a PCI Express device, the CPU or the other devices in the system, they cannot cache it. Basically, the coherency doesn't extend beyond that interface. So that's first set of problems. There are 4 sets of problems that we are looking into with CXL. So first is that heterogeneous compute model. Second is we all know that we are up against the memory wall, which is that if you plot the amount of computation that you are getting from the core, if you plot the number of cores that you can put in a CPU socket today, and if you plot that against the amount of memory bandwidth available per core, that's going down. So ideally that should be keeping up or going up, right? And it's not that we are not improving the memory speeds. Of course, DDR speeds are going up. We are adding more and more DDR channels into the platform. But fundamentally, with every DDR channel that we add, it's about 300 signal pins. And you get about 50 gigabytes per second, right? If you look into our CPUs today, we started off not too long back with just one memory channel, then we went to 2, then we went to 4, then to 6, to 8, on and on and on, like 16, it's still there, right? There is and with the DRAM being placed so close to the CPU, it's a thermal challenge to cool those things, right? So that's the other part of the problem, and then the corollary to that problem is that the cost of memory in terms of per gigabit, that has flattened. So as you need more memory is now becoming an increasing part of the overall system cost, right? Third aspect, which I'll introduce the third and the fourth when the time comes. So first these two, right? So these are the direct attached model that we solved with CXL. The other aspect of it, so what we need is then 2 additional protocols. One is of course .cache so that devices can cache the system memory if they have a need for it. And the other aspect of it is .mem, which is the memory protocol, which means that memory attached on CXL can be mapped into the system coherent memory space, right? Now, if you put caching semantics and memory semantics, then of course, your latencies need to be lower. Right? You can't have very high latency and have these semantics and expect that the system performance will not be impacted, right? And of course, how low of a latency? Well, ideally what we said is that your latency needs to be similar to that of nearby CPU socket's memory. So just like a NUMA, right? I mean, so imagine you're in a multiprocessing system. You have a certain latency if the memory is attached, DDR is attached to your local CPU socket, which is about 100 nanoseconds. Again, we'll talk in round numbers here so that we don't have to give somebody a particular implementation's number. If you go to the nearby socket, let's say it's at 200 nanoseconds, right? Another 100 nanoseconds. So as long as the access looks similar to that of a NUMA node, we know how to handle that, right? So that's basically where the low latency requirements come from. And last but not the least is asymmetric complexity. And by that, what we mean is, in this picture, if you look at it, there is the notion of a home agent. What is a home agent is basically something that is very detailedly involved with the internal microarchitecture, but it orchestrates cache coherency between, for example, different caching agents in the CPU. For example, any CPU today has got multiple cores, multiple levels of caches, right? So it is orchestrating cache coherency. Even for your non-coherent protocol like .io, behind it there is a caching agent, because somebody needs to make sure that your cacheable system memory looks consistent with the non-cacheable view from the device point of view, right? So that's a given in any given system today, right? Everybody has a home agent that's responsible for orchestrating cache coherency, for resolving conflict between different coherency agents. So what we said is that the home agent functionality stays with the host processor, and what happens is on the device side you get a very simple set of literally a dozen set of instructions, which is like, I want to read this cache line shared, I want to read it exclusive, right? And anytime I do anytime I've updated that cache line, I want to do a write back. A CPU can send me a snoop, but then beyond that, the devices don't know anything about orchestrating cache coherency. So asymmetric complexity helps ease that burden, right, on the entire system. And this is something that if you look into the home agent functionality, even for the same company over multiple generations of processors, they change quite a bit for good reasons, right? Because again, your underlying microarchitecture changes, so things do change. And this way we isolate the devices from the wide variety of home agents that are going to be out there, and different architectures do things very differently. Even within the same architectures, things get done very differently at different points of time. So that's the fundamental approach of CXL. And here are some of the representative usage cases, and we call them as three types of devices: type 1, type 2, and type 3. I'm glad that, yeah, so type 1, type 2, type 3, that's basically what you have up there. We're not marketing people, so that's the most creative names we come up with. Type 1s are basically your caching devices and accelerators, and fundamentally they have the .io, which is the PCI Express like protocol. Everybody has that. And then you got your .cache, which is the caching semantics that's built into the CXL protocol, right? And the usages are things like accelerators, SmartNIC. So things like, for example, if you're doing partition global address space NIC, there is a certain type of ordering model which is different than PCI Express. So what happens today is that if that ordering model is different, then what will happen is if I get a read, I have to let the read complete before I'm going to do the write, because writes can bypass reads in the PCI hierarchy. Now with caching semantics, I can issue a bunch of prefetches, but then execute them in the program order that I desire in my local cache, which has got a much lower latency, right? So that's basically a way for me to get better bandwidth. Same thing you can do with atomics, like you can do a lot of very advanced atomics without having to make sure that your flavor of atomics is there in each and every one of the CPU. Once you get locally into your cache, then you can do whatever atomics you want to do, like double precision floating point atomics or whatever other type of atomics you want to innovate on. Second type of usage is around the accelerators with memory. So these are things like your GPU, all those things where not only are you want to cache the system memory, but also you have memory that's attached to the device side, and you want that memory to be mapped into the system coherent space. So that way, you can do the proper placement of data depending on who is going to use the most amount of data, but then everybody can see that data without having to move all the data back and forth. Last but not the least, and this is where we see a lot of interest, is around the memory buffers, which is type 3 devices. Like as I mentioned, we are up all against the memory wall, so memory bandwidth is not increasing. Now imagine if you can put memory on the SerDes based ports like PCI Express, and that gets mapped into the system coherent space. Now remember, 300 signal pins for roughly 50 gigabytes per second. And now contrast that with, if you look into a PCIe Gen 5 when we first introduced this, and now Gen 6, which is twice that amount, right? Your amount of bandwidth that you are getting is 128 gigabytes per second, both directions, for 64 signal pins. And if you, that's the raw number, right? And then if you double that with Gen 6, you get 256, right? So it's, per pin efficiency wise, it's just much better to do serial pins. Now the downside is, of course, nothing beats the latency of a parallel bus. Okay, so you're going to be latency wise at a disadvantage, but there is a how many 300 pins are you going to keep on adding into the platform in a thermally constrained environment? So the other good thing about the memory buffer here is that it is memory technology independent. So you can have, for example, DDR5 in the in your main DIMM, but you can put DDR4 over here. You can put even some advanced type of more cheaper memory that you can have as a capacity expansion on CXL. So you can use it as a bandwidth expansion as well as a capacity expansion, and you can do your mix and match depending on what you want to do. And Mahesh and others will talk a lot more about these. So that was CXL, the first generation, right? So now let me switch gear and talk about the second generation. And this is the time I can introduce the third problem statement that we have, and that has to do with stranded resources in a data center. By that, what I mean is, so let's look into the picture here, right? So you have the hosts, right? Multiple hosts on the top side. Imagine that each host is like a full-blown server, right? It's like a 2 CPU socket server connected to its own memory, right? Even though it's a small box, that's what it's supposed to represent, right? It's a full-blown server on a chassis by itself, connected to its own set of accelerators. And with 2.0, you basically put a CXL 2.0 switch, and on the other side you have a pool of memory or even a pool of accelerators. Okay, now what's the problem with the stranded resources? Well, each and every one of the hosts today, right, it's a tightly coupled model, the load store, right? So if you put memory next to, for example, a CPU, so let's say I have a 2-socket system. For argument's sake, I have a terabyte of memory. Most of the time we find that people don't use that full amount of memory, and generally people have to over provision, because if you need more memory, there is no way for you to generate more memory in the field. I know Siamak is working on that, but that will take him a few decades probably. No, just jokes aside, right? Because you need to over provision that. So but on the other hand, if I get a task that, let's say, needs 2 terabytes of memory, what do I do? Well, I have no choice but to go through page misses and suffer the performance consequences, because again, I cannot create memory out of thin air, right? So I got the problem of stranded resources. I got the problem that I cannot run tasks efficiently that do not fit within that profile. And you can make the same argument even about accelerators, right? I have a certain task that might need, let's say, X number of accelerators. I put, let's say, 8 accelerators, let's say, in my server, and somebody needs 16. What are they going to do? Well, you just have to make do with 8, right? Now the challenge that pooling helps us overcome is that you have resources that are captive to those hosts. That doesn't go away. But in addition to that, you put some additional resources on this other side of the switch. And what that does is that whenever there is a need, right, whenever there is a bandwidth demand or a capacity demand, right, or a processing demand, you can come to that other side of the switch, get the resources that you need from the pool. Once you're done with that, you release it back to the pool. So now maybe the memory that you have, a terabyte of memory for every server, instead of that you can put half a terabyte, and then you can put the rest of them over here on the pool side, and now you got a better usage of your resources that you can do. So that's the problem that 2.0 solved. And not only, so then the question is, what is the unit, right, in which these resources move? Of course, we can move the entire thing by a device basis, but for memory, what we did also was we defined things called a multi-logical device. And you'll see that the color combination, right? So you can see like D1 is completely assigned to H1, but D2 is assigned partly to H1 and partly to H3. So you can do different locations as get assigned to different servers up to 16 at CXL 2.0. So this is the first time that you see a load store kind of tightly coupled interconnect has been used across multiple sets of servers, right? And there are challenges with that. Of course, there is the latency challenge. Your latency will be higher. But like anything else, it's a trade-off, right? Your latency will be higher, and also from the things that are below the switch, those are, you need to be careful to make sure that you are maintaining isolation between the different hosts. Let's say a host goes down, you need to make sure that not everybody else will go down with it, because they are pooling some resources, right? So, and we built all of that into the CXL 2.0 specification. Same thing with the quality of service. All of those things you need to work through, right? Of course, with 2.0, we went with a single level of switching. 1.0 was a straight direct attach model. 2.0 was a switching model that we enabled. So this enables for memory expansion and of course connecting more of the devices. We talked about 2.0 enabling resource pooling, resource disaggregation, and effectively we have this managed hot plug flows to move the resources around, right? So whenever you need more, it looks like a hot add. Effectively, it's like an onlining, right? But it goes through the same process. So you add resources. Once you are done with that, you release it back. So it's like a remove, which is offlining. So all of those things we can do, and then we also added things like persistence flows with 2.0 for persistent memory. We defined things called like Fabric Manager and API, which these gentlemen will talk about for managing the resources. There were security enhancements. Security is a never-ending thing. You always keep doing more and more, right? So authentication and encryption is what we did, and effectively, as I said, right, 2.0 is the first time when we went for a load store interconnect from a node level to rack level of connectivity. So far we talked about the three challenges, right? That we have solved. The third one with CXL 2.0. I'll talk a little bit about the fourth challenge. And so this one is, so 3.0, what we saw when we started 3.0 is that we have the, nobody's ever happy with the amount of bandwidth they get. Okay, people will always want to keep doubling, paying half the power so that the power remains flat with the same latency, right? I mean, these are all good things, and the different standards bodies are here to solve those problems, and those are hard problems. So, of course, we double the bandwidth on a per pin basis. And we talked about reduced memory capacity, bandwidth per core. That was part of the second problem statement, so that still remains. So that's being helped by the bandwidth doubling, and then efficient peer-to-peer resource sharing across multiple domains. So this is talking a little bit about the fourth problem, and then we talked about memory bottlenecks, right? So which was the second problem. So fundamentally, the fourth problem is that yes, we have pooling, right? We talked, so that's the third problem. Let's say, no more stranded resources. But then the question is, for every access, if I go through the CPU, then I have a bottleneck there. Ideally, you want things to be distributed, and yet that flies on the face of saying, hey, everything is asymmetric in nature. So, you can't have your cake and eat it too. Well, it turns out you can. So, we want to only when needed, what we want to do is involve the CPU. Otherwise, you want to basically have multiple paths between any pair of source destination nodes. And, doesn't matter whether it is the memory that is mapped into the system memory space or whether it is a device that you are trying to access, right? You should be able to access them without having to go through the same path, right? Because if you always take a fixed path between source destination pair, that forces you to be in a tree topology, which we know it's good, but it's constraining, right? You want to go to more of a fabric topology, which is the fourth problem statement that CXL 3.0 solves. So what we did is with 3.0 is we introduced fabric capability, which is that yes, tree topology will be there for people that really need it, and it will be there for the initial discovery and all of that. But beyond that, there is a fabric capability that we introduced. We need improved capability for better scalability and resource utilization. In other words, single level switching. If we can expand that, then we can construct larger composable systems. We talked about doubling the bandwidth, latency being zero add, and of course maintain full backward compatibility. So you can take a look into this. This goes through some of the features, right, that we'll talk about some of these, but effectively we'll see that there is a set of things that we introduced for the first time in CXL 3.0. We'll talk more about that. So how much time do I have? I'm doing good in time. No, too early to say. All right. So, CXL 3.0, we double the bandwidth with the same latency. And effectively, what happens is that going from, what we have done a lot of analysis, NRZ signaling pretty much becomes ineffective beyond, some will argue 40 gig, some will argue 38 gig, some will say 36 gig. Okay, fine. Beyond 32 gig, I think it's pretty unanimous that NRZ becomes a challenge, right? So when we went with PCIe 6.0 at 64 gig, it was PAM4 signaling. And it's, PAM4 is nothing new. The networking world has done it. They tend to be, thankfully, at the bleeding edge of technology. We are at the leading edge of technology. That's how I call things. So, PAM4 signaling means high bit error rate, and, the thing that we did not want to inherit from the networking side is the high latency of the forward error correction. In other words, if we add 100 nanosecond for FEC latency, FEC decoding and all of that, for a lot of these applications, it's just a non-starter. So you'll notice that, the amount of time we allot for a read to the data coming back for a memory type 3 device, that's 80 nanoseconds, right? I can't add 100 on each direction to that, right, and still be viable. So what we did was, so there are three pictures here, and we can go through this in a lot of detail, but I don't want to lose my bet here. So on the top you have the 6.0 flit layout, which is, you will see that it's a 6-byte FEC, which basically it's 3 levels, 3 independent forward error correcting codes which are interleaved, so that way you're taking care of the burst, right, effectively. So that results in a low latency forward error correction. You're correcting a single symbol within each FEC group, and then you got 8 bytes of CRC, which is fairly robust, right? 8 bytes of CRC guarantees 8 bytes of errors that will be detected, and beyond that, more than 8 bytes, you have a 2 to the power minus 64 is the statistical probability that an aliasing will happen. So with that, your fit rate is practically 10 to the power minus 10, which is, you're going to have that many escapes in a billion hours, right, which is practically zero. Your silicon has 3 digits, 4 digits fit to begin with. So this is 10 to the power minus 10. Or in the case of CXL, the latency optimized one, it's minus 3, which is still pretty good. So, excuse me. So what we did with CXL is that there are two of those, right? So the second one and then the third one, there are two sets of flit layout. The first one you will notice is similar to that of PCI 6.0, so it works on a 256 byte granularity. And then the one below that is a more optimized version that we did for CXL. You will notice that there is 6 bytes of CRC for every 128 byte. So what we do is that you accumulate 128 byte, you just do the CRC check. If it passes, you use the data. You don't wait for the next 128 byte. If there is an error, then you wait for the next 128 byte, you do the forward error correction, then you apply the CRC, and if it is good, you accept it, otherwise you go for a replay. Right? So what we are really trying to save here is a couple of nanoseconds, really, literally. One of them is, of course, there is the accumulation time of the entire 256 bytes. So with the latency optimized flit that you have, a 128 byte accumulation is half the time of a 256 byte accumulation, and if you did the math with respect to a 68 byte flit at 32 gig or 128 byte flit at 64 gig, right, accumulation time is slightly better, not by whole much, but fine, it's the same as what we had with 32 gig, right. And then I'm not doing any effect for the most part, right? I'm just doing a CRC check. How many levels of logic is CRC? It's about 6 to 8 levels of logic, which is practically nothing for doing the thing. So anytime there is no error, you are going to accept the packet. Anytime there is an error, you have to now pay for the accumulation latency and then the FEC correction latency, which is, like I said, we are trying to save on those couple of nanoseconds in case FEC needs to be involved. Okay. And then if that still fails, then of course you have to go through the replay. Okay. So that's basically what we did with CXL 3.0. There are two types of flit, is the key takeaway. One of them is the 256 byte standard flit, looks very similar to PCI Express. The other one is a 256 byte flit, but with some latency optimization flavor. So that's how we went to 64 gig PAM4 and kept our latency flat. Next one is around protocol enhancements, and there are two simple constructs, but these are very powerful constructs. One of them is known as unordered I/O, and the other one is known as back invalidate. So remember, I said about the fourth problem statement was direct access, not everything needing to go through the CPU. So unordered I/O, fundamentally what it says is that, hey, I can access memory, or I should be allowed to access memory directly by going from the device. If it is coherent memory, right, I can access them directly by going to the place where the memory is, if there is a way for me to figure out if that memory is being held in a coherent state that is consistent with what I want to do. And what I mean by that is, for example, if I'm reading a memory location, I should be able to go and access that memory directly without involving the CPU if I know that that memory location is either invalid in the rest of the caches, which means nobody has it cached, or at most they are shared, in which case I should be able to go and get it, right? The only time I can do it and I need to involve the CPU to resolve the coherency is if I want to read a copy, but then that's being held as exclusive because I don't know whether that's the latest or the greatest copy, right? So unordered I/O, fundamentally what it says is you should be able to send your I/Os, and these are I/O coherent, right? These are not they're not allowing you to cache it. If you have to cache it, then you go through the proper CPU hierarchy, go through all the resolve the cache coherency, but those take quite a bit of bandwidth just to resolve coherency actions. But I should be able to go and get that location, and I should be able to process it. The question is, okay, what happens when you go to that memory and let's say the memory location, it maintains directory anyway because that's part of CXL. It finds that, it's a couple of directory bits, it finds that, well, somebody might have this location. It's not a guarantee that they will have it, but they might have this location, and we need to resolve your coherency conflict. Well, remember, these can be type 3 devices. They don't even participate in cache coherency actions, right? Why does a memory device need to understand anything about cache coherency other than it looked at the directory and said, hey, I think somebody has it. So what we did was we introduced the notion of this thing called back invalidate, which is part of the CXL.memory flow. All that it does is the memory device tells the host processor saying, I have this access that's coming on the side, and I think there is a conflict. Why don't you get into action, do something? So then the CPU of course knows how to resolve coherency. It's going to do a bunch of things and then tell the memory side that, hey, now you can go and do the transaction. In the meanwhile, what has happened is that particular transaction, the memory device or type 2 it can also be a type 2 device, right, has put it on the side while it is processing other requests, and off you go, right? And the reason you can do that is because these are all unordered. So what happens to the ordering model? Well, the ordering model moves to the source. By that what we mean is, if it is a read, of course you know when you got the read completion, so no prizes for guessing that. Now if it is a write, what we did is, instead of writes being posted, you get a completion back for that write. So that tells you that that write made it, and then you can post whatever flag and whatever else you need to do. So in other words, before you tell the rest of the system that these writes are all committed, you have waited for that handshake to come back to you. So those are the two things, right? Very simple construct, takes advantage of all the existing mechanisms that we have, right? Same kind of virtual channel, same kind of everything, right? But very powerful construct. Now what it did is it enabled me to do direct access, and also it enables me to do fabric topologies, right? With two simple things, we are able to remove the shackles of the restrictions of a tree-based topology, while still maintaining all the architectural ordering semantics that we like to do. Yeah.
What would be one use case for UIO?
So let's say so question is, what would be a use case for UIO? So let's say that you have a something coming from your NIC, let's say. Okay, so let's say you got a packet coming in from the NIC. It's targeting a memory location, and you might have to do some amount of processing. Now question is, do you want to take all of that into the main CPU and then do the processing, or can you do some processing next to the device? Let's say could be your GPU, for example, that's hosting the memory. So now the NIC, it looks at the address, it says, hey, I know where this location is. It sends it to the proper GPU or the type 3 memory device. The memory device does the processing, and once it's done the processing, it basically loads it into the memory. Now contrast that with what would happen today. You would send it to the processor, you're going to queue it up there, it's going to go back to that location, get that data, right? It's a lot of movement back and forth. You just have removed all of that movement back and forth. The processor will do the processing and then finally do the write back into the memory, right? So you have just cut everything out of it, just gone directly. Now there is a small chance that that memory location might be held by somebody in their cache, but that's very rare, right? That it's unlikely that you're writing to something from, let's say, coming from the NIC side, that somebody else has it. It's possible that you can have a stale copy, but even if it is a 1%, 2% case, you'll still, if you do the math, you're going to come out way ahead in terms of your bandwidth utilization. So that's an example, right? And then the other usage is, like I said, I can do non-tree topologies. That's the bigger one, right? So this particular one talks about how to build, even for the UIO and the back invalidate. How can I build Snoop filters in my type 2 devices? So today, for the amount of memory that you have mapped into the system memory space, right? With CXL 1 and 2, you had to have either a directory to track, or you limit the number of entries that are part of the system coherency space, because otherwise there is no way for you to really invoke something. And with 3.0, what we did was we enabled this notion of back invalidate. So you can now have a Snoop filter, and anytime you are having a capacity miss, you can basically issue a back invalidate back to the processor, so that your Snoop filter is consistent with whatever is there in the processor, right? So this just goes through an example flow of that. Effectively, it's like a capacity miss, you are going to issue a back invalidate. With 3.0, again, we support multiple levels of switching. So this is just showing an example of multiple levels of switching. And the right side one is a tree topology. So that's of course supported. But then the left one is a non-tree kind of topology. So we support that also. So multiple devices of all types per root port. That's again an expansion of what we support. The other aspect of CXL 3.0, in addition to the pooling, right, which we did in 2.0, and this is like pooling at a much more larger level of system, we also have this notion of what we call shared coherent memory across multiple domains. So far, pooling means that, each of those locations, if you want to look into those, right, they belong to one given host, right? In other words, no two hosts see the same physical location of memory. That's pooling. Now, there are lots of applications where you want to have a set of memory locations that are shared in a coherent manner between multiple hosts, so that way you can pass that as semaphores or whatever, right? You can pass data structures back and forth between them if you are working collaboratively on a problem. And 3.0 introduced this notion of the shared coherent memory, again because the fundamental problem is that each of the hosts is an independent coherency domain. They don't know about other hosts, right? For example, every host thinks that address location 0 to whatever belongs to them. They are in charge, right? And you can't have multiple sets of people thinking that they are in charge of the whole thing, right? So it's much easier on the other hand, for a device, because we have the backend validate, the device can be told that, hey, these locations are shared between these hosts. So now it can track them on its own local directory. So anytime there is a conflict between multiple hosts, it can just independently issue backend validates to those hosts and resolve coherency without really orchestrating the coherency conflict directly that way within each and every one of the hosts. So that's basically what we did, and we defined this thing called global fabric attached memory that this gentleman will talk about. I think more of the same stuff. Let's see here. So again, CXL hardware coherency is enforced for this shared coherent memory location. Now 3.0 introduces this notion of, as I said, fabric, right? So what you see in this picture here, it's a non-tree topology, right? In other words, pick any source destination pair, you've got multiple sets of paths. And that way you can do a better job in terms of doing load balancing. You can do a better job in terms of getting more bisection bandwidth, right? So all of those things you are going to benefit tremendously. And you can basically now use CXL truly to attach to have something like these switches can be they can be leaf switches or the spline switches, right? You can be on the top of the rack or middle of the rack, especially given that copper cables are about 1 meter is what they're extending. Maybe you can do it in the middle of the rack, right? Or if you want to do an optical transition, you can be few racks away. But fundamentally now what can happen is that all of these are resources right at the bottom, right? You've got accelerators, memories, CPUs, all of those. You've got GFAM. Not only can you pool resources that you can go within your rack or even across racks and get access to it and build composable system, right? I can build a system with, let's say, I got a 2-socket server. I need more memory. I can go somewhere, get the memory attached to it. I need more accelerators. I can go, to another chassis, get some amount of accelerators, and I can attach to these in a dynamic fashion, right? You can do this as a dynamically composable system. I can also have things like an HPC problem where I got multiple independent servers that are working on a problem, and then I just have a global fabric attached memory that I can use as an area in which I can pass intermediate results back and forth between all of these different hosts. So that's what CXL 3.0 enables, right? So it's, as you can see, it's a crawl, walk, run philosophy, right? Start with something, get the traction, do the learnings. We're still in the learning process, by the way. We're not past this thing, because if you look into the ecosystem, people have started deploying CXL, and so there will be more learnings, and we will incorporate, right? It's a part of any learning organization, but gradually we are solving these challenges one after the other, surely, but definitely in a timely fashion. So that brings to the end of my presentation. Any quick questions? 45 minutes on that topic.
Go ahead, can I just talk for a second?
Sure.
Thanks, I'm not part of the show here, but I'm the chairman of the CXL Consortium.
All right.
And I want to thank you for registering, being part of this. And the mic's a lot low for me. I'm 6'7", so I'm a little bit taller than Devendra. So
Just a little bit.
But anyway, Devendra did a great job. I've presented these slides many times, but nowhere near as well as he does. But I've been involved with CXL from the inception, and it's been fun to watch and to help lead. And I just want to make a point that CXL is an open industry consortium, so any company is free to join, able to join, I should say, not necessarily free. But we actually, one thing that's very, very unique in this industry is CXL, the adopter tier, is free. Most organizations do charge. So we have a free tier actually to be a member of the CXL consortium and get all of the IP benefits that these large consortia employ. So if you're not a member, well, if you are a member, thank you. And if you're not a member, you can join. And even at the contributor level, where you could work in the groups, it's one of the least expensive. One of the reasons being is because it was very, very clear that CXL was going to take off like a rocket. And when you have a small consortium, you need to charge a lot of money because there's fixed costs for any consortium. As it gets larger, the cost per company decreases, and we saw that happening and everything else. So I'll reiterate, Devendra talked about crawl, walk, run, and then we have sprint. Then we have driving cars, and then planes, trains, and automobiles. We are, this is going crazy. And it is one of the hottest technologies, I think, in the industry. So I'm glad you're here to learn about it, and thank you for coming. Back to Mahesh.
Thanks, Jim. Talk about time pressure. So I'm running into two things. We said we're going to give a break at 10, so we'll try to wrap up right around that time and see how it goes. So quick introduction, my name is Mahesh Wagh. I'm a co-chair for the CXL Consortium's technical task force. I'm an AMD senior fellow, so I drive all of the EPYC server system architecture, and my team drives some of the CXL execution. All right, so we're gonna dive deeper into memory pooling and sharing, go into some of the aspects, especially cover some of the things that were introduced in 3.0. So we'll start with I'll be focusing more on memory devices and sort of CXL.mem, but some of those concepts are applicable to the other device types as well. Quick background, so I think this topic, to do justice to that, let's just start with a quick background of what an SLD means. This is single logical device, right? This is your memory device. It's got only one link coming into it. It's got memory resources. This is what was defined in CXL 1.1. Right? It's a primary function. You can identify that device through CXL, DVSec ID. You get lots of questions in terms of, can this device be a multifunction device? And yes, any of the CXL devices can be multifunction device. You have the non-CXL function map DVSec that just says what the other capabilities of those devices are. And this device, from its definition, must support 1.1 so that you have the backwards compatibility. All of your investments into it, you recoup your investments by supporting backwards compatibility. And The type 3 device component registers define the HDM. This is the host defined memory, right? So the key aspect is all of the memory media that is behind CXL, you have to map into some memory space, right? And as we talked about, you map that memory in the host physical address. So you need a way for the device to understand where that memory is mapped. So you do that using the HDM decoders. And such a device typically is connected to a single virtual hierarchy. What we mean by that is it belongs to a given virtual hierarchy domain, it gets mapped into it. So the key things about talking about this device was, as the definition was starting for CXL, you had an understanding of how to map CXL memory devices into a given host system address space, right? A lot of infrastructure was getting built on top of that. But at the same time, there were a lot of use cases that said we want to extend this use case. Devendra talked about all of the motivations to get into pooling and sharing. So important aspect was, how do you keep something that you've defined about how to map this memory in a system address space, and then extend on top of that by adding pooling and sharing, right? So the concepts get started defined by SLD, and then we build on top of that. So that was sort of the story behind that. And then pooling was introduced in 2.0. Basically pooling, think about it this way: you have a device with media. You want to partition that media into n number of partitions, and then you want to assign that partition exclusively to given host image, in which case you're mapping that partition's memory into a given host image's system address space. That's what pooling was about. We defined a device that was called multi-logical device, in which case you can take a single device and share it across multiple hosts. And there were semantics that were added to the protocol to support that. And we'll go deeper into that. From a scalability perspective, it was supporting up to 16 hosts. And if you're attaching an MLD device, then you needed a switch in between, because the switch is what understood that it can connect to multiple different hosts and then pool this device, right? So that was a concept that was introduced with CXL 2.0. Now, as we were doing this definition, there were a lot of pioneers, a lot of them are in this room, who were looking at it and saying, well, even with 2.0, you can really do pooling, you don't need a switch. You can define devices that could directly attach to a host without requiring a switch. There were also concepts of, hey, if I'm pooling a device, isn't it just a natural extension for me to share a device, right? So all of those things were getting discussed in 2.0, but we had to get the 2.0 spec out and then look into the developments that are happening in the ecosystem and bring those concepts that people have already talked about into 3.0, right? So that sort of starts the stage into, what's 3.0, and yes?
So you didn't show an example of multi-header device?
We'll talk about that, yeah. So we'll get more into, but as we get into that, it's really good to ground ourselves on all of the definitions, because now you're getting into the space of what does pooling mean, what does sharing mean, what's the scale, right? So it was really important to define some terms, right? So we'll talk a little bit about what those terms are and then get into that, right? So basically, if you're looking at a memory resource, and if that resource is connected to multiple hosts, we call such a device or that memory as fabric attached memory, right? Which means you have more than one host that are accessing that memory. And that memory is called FAM. We expose that FAM via logical devices, because now you have some resource that's virtualized and handed over to a given domain. So you look at that and say it's FAM, and then every host image is going to have a logical representation of that device. So that's why it's exposed through logical devices. And we talked about scale. You can get up to 16 partitions with, just CXL 2.0. What if I want to get to thousands of partitions, right? And share it across thousands of nodes. If you want to get to that level of scale, then it's exposed in a more scalable manner. It requires you to have different sorts of routing, which is called port-based routing. Vince is going to go talk a lot more about fabrics and how it is. But if you have memory that is supporting scalability at that range, we call that type of memory as GFAM, which is global fabric attached memory, right? So it's just talking about the scale. Now, when a fabric attached memory is dedicated exclusively to a single host, then we call that particular memory pooled memory or pooled fab, right? So pooling means it's a resource that's exclusively mapped into a given host domain, right? An example for that is that S1 that's in partition, and you have that pooled across, S2, which is pooled across, the host H2, right? So it has a copy of that. If it's shared fam, then it's only attached to one host, right? So that's what it is. Now, when we talk about pooling and sharing, especially when you talk about sharing, you also have to talk about the concepts that are important to guarantee the coherency model for that, right? And you can support sort of two coherency models associated with any resource that you take that is shared between multiple hosts, right? What I mean by that is you have the same physical address range, right? Like the device's physical media mapped into two different host images, and they can concurrently access that memory, right? Now, when you have such a thing, you have to talk about coherency. We have two ways of solving that. One is software coherency, and the other one is hardware coherency. Software managed coherency means that you're managing the ownership of that particular region through some means that are outside the scope of specification, in which case you're defining some data structures, some locks, some semaphores that you can say have exclusive access, and then anybody who has an exclusive access can write to that memory, everybody else can read, right? So it requires some very close coordinating at the software level, but you can deploy those models, and you can see hopefully in the event and in the past events, a lot of companies have explored that space and talked about how software coherency can be enabled with devices and systems that are available today. When we get into the next level, which is we really want to get into supporting multi-host hardware coherency, right? This is where you're saying, we're not going to rely on software-based coherency mechanisms. We want hardware to provide the guarantee for coherency. Then that requires some unique hardware flows. There are some specific flows that you have to go into and make sure that those are required for coherency, right? The shared region must be mapped as HDMDB, right? This is where you map it as HDMH or HDMDB. Right? And then you support the backend validate channel. So this is where you can, Devendra talked about what BI does. So when you're having something that is multi-host hardware coherency, you need to support BI. And if you are interested in your use model requires you to support direct peer-to-peer, we talked about the advantages of direct peer-to-peer, then you need to support unordered I/O so that you have access, so that you can get some of the benefits of direct peer-to-peer access. Yeah.
So how do I know S2 is really pooled fab?
Yeah, I realize there's an issue in this one. I need to change that diagram, but yeah. S2 should just go map to H2, right? In that case, it's just one exclusive copy of that. Yeah. Okay, so let's get into then, what is the definition of a multi-logical device, right? And then we'll get into MLDs and other things. So when you look at something that's a multi-logical device, in which case it's a FAM type 3 device, and it can partition all of its resources, and it can partition up to 16 resources. We call each of those partitions as LDs, logical devices. And you need a fabric manager. And you need a fabric manager FM-owned LD. And the reason for that is when this device comes up, you need something that comes in and programs this device, programs its partitions, and then allocates it to a given host, right? All of that functionality is done by a fabric manager, and the fabric manager accesses this device through the FM-owned LD to go program this particular device. Now, as this device appears in a given system's image, it appears as if it's a type 3 SLD device, right? So the switch does all of the magic in between to map the logical device to a given virtual hierarchy, and then that particular device appears to the host image as an SLD device, which means anytime you're doing a config access, an IO access, an HDM access, at the software level, you won't be able to distinguish between an SLD or an MLD device, right? That's just exposing its SLD partition, right? The FM mode LD is accessible with the specific logical device ID of all ones, right? So on CXL.io, you send that out on a TLP prefix, and that way you can access the FM mode LD. You use the CXL.io path to go program all of the partitions and then configure the MLD device. The MLD link, so how do you know this device is an MLD device? So when you go through the auto protocol negotiation, as part of that, you advertise that you're MLD capable, and then you negotiate the MLD operation. So now you know that you're an MLD device. One of the questions that I get usually in this particular section is, after you configure, how do you know, are all the accesses done with the LDID? And the answer is yes. Once you negotiate to operate in an MLD, then all your accesses, whether it's CXL.io or if it is CXL.mem, then you're carrying the logical ID on all of your transactions so that the device can identify that. And same thing with CXL.io. You have to carry that in your CXL.io so that the appropriate logical device can access it. Right? So that's how these things are carried forward. Now, we'll introduce like CXL 3.0, a lot of things that were possible in the ecosystem. We wanted to make sure that the specification covers it, which is, if you're thinking about the shared or pooled device, one way to think about it is like what we talked about the MLD, right? You have one link, and then through that link, you're accessing this device and you're partitioning this device, right? But you could think about just saying, I can expose these multiple heads to to a given host directly, and I don't need to put a switch in between. You can save some amount of latency by doing a system like that, right? So in that case, you have multiple links coming out of the device, each link directly attached to a given host, and then you pool the device, right? Or share that device between those hosts. Again, the same concepts apply. Your partitions would still be available to each host. From a host perspective, it would look like you're connected to an SLD from your image perspective. A couple of things that were added to this was there was a LD pool CCI. There's a command interface that was defined so that the Fabric manager can identify that and then go program these devices. Right. So as you can see now, we've introduced these concepts of I have an MLD, which is single link, and I can partition the resources behind it, or I can give you multiple links, right? From a multi-headed device perspective, this is just getting into more aspects of it. Just to illustrate, right? You have, as an example, 4 links coming out of the device. You have a host physical address. Each of those links will have its associated HDM decoders, and then you have memory resources that you're partitioned and assigned to a given host, right? So if it's a pooling example, this is a 4-ported CXL memory device. It got 4 links. And then in this example, we're equally allocating those pools across the 4 hosts, right? But you can allocate in any fashion that you want, depending on the needs of the system. Now, there is this concept of a multi-headed SLD. And now this is adding more terms on terms of what's possible, what are the systems you can build, right? And then there is a multi-headed MLD device, right? So if it's MHSLD, then in that case you have multiple heads. Each head has a logical device associated to it, and then you're connecting to a fab, right? And heads can directly attach to the hosts, right? So that's a multi-headed device, MHSLD. Now if it's a MHMLD, this is a multi-headed, multi-logical device, in which case we have those single heads, right, single ports, and then each of the links that you form with that port can be an MLD device, right? So in this example, you have head 0 connected to logical device 0. It's an SLD, right, MHSLD sort of thing. But head 1 has 3 logical devices, and it's looking like a multi-logical device, right, because it's got 3 partitions in it. Right? And that's where you can connect that device. So on and forth. And if you're using a device like this, then it requires a switch for that MLD functionality, right? So any link that you have that's an MLD link, you will have to connect to a switch, because the switch is the one that understands MLD. The other ports, they could directly connect, if it's MHSLD port, then that can directly attach to a host, because all it understands is there's one logical device behind it, right? So that's sort of the way to think about these devices and think about how you can construct one, right? Now the question is, how do you manage the multi-headed devices, right? A lot of work was done for using the MLD framework, right? So MLD framework was defined in 2.0 that just said, you understand how multi-logical devices are, you understand the partitions, and then you have ways to manage and map those partitions. So that same thing was extended with this LD pool CCI. So with that LD pool CCI, you can identify the logical devices and then do the mapping of the logical devices to the associated heads, right? So I think in the programming section and in the fabric section, we might touch on some aspects of that. And then finally, we'll come to an example of a GFAM device, right? This is what we talked about. You want to get the scalability really high. You have a memory resource, and you want this resource to be accessed with many, many nodes, right? How do you enable that? In that case, you need a fabric, and Vince is going to talk about how this fabric is formed, what's the scale of that fabric, right? And the same concepts apply. You can have this GFD device that could be single host mapped, in which case, some portions of its memory you're exclusively mapping, and it could be multi-host shared, right? In which case, that same memory region can be allocated and shared across multiple hosts. The same concepts, peer-to-peer access. If you want to provide access to this from a peer device, you can support UIO getting to this device. There are some unique differences between how a GFD device appears versus the other GFAM devices, right? A GFD configuration space is only accessed by FM, and the memory capacity for a GFD device can exclusively be managed using dynamic capacity mechanism. So we'll touch on a little bit about the dynamic capacity management, how it is used, and so on and so forth. A lot of host client management of GFDs, it's expected to be covered in future ECNs. We should see some of that come up with the upcoming CXL 3.1 spec. So today we're not going to go a lot into the GFD management, but just wanted to introduce the concept of what a GFD device is from its scalability perspective. And the key thing is, if you're a GFD device, you're using a different routing mechanism. You're using port-based routing to access the device, right? So that's what it is. At a high level, what are the differences between an LDFAM and a GFAM, right? If you look into it, there is the introduction of what's called device media partitions. So you take a device that's GFD, you take its media and divide it into partitions, and then you map those partitions into the host physical address. And then within those dynamic capacity regions, your device physical address, you uniquely tag it as either it's shared or it is exclusive to a given host domain, and that way you can map it to a host domain. I won't read through all of this table, it's there in the spec, but just some differences there, like with LDFAM, a given device, how many hosts can you support? Up to 16. GFAM gives you, thousands architecturally, probably hundreds from a realistic implementation perspective. And then there are some other differences in there in terms of just how that memory is done. I think I touched on the routing and address decoders, right? That's, you have to support, port-based routing if you're using GFAM versus the other schemes that are defined in CXL 2.0 apply to the LDFAM devices. We'll touch on Fabric Manager as we look at any device that is pooled or shared. You need some resource that is coming in and configuring those devices, right? That resource is typically a Fabric Manager, and that connects to a Fabric Manager endpoint in the switch or a device. Depending on the type of device, you'll need one connection. Definitely a switch that is supporting pooling and sharing will also require that. The functions of the Fabric Manager are to identify pooled devices and shared resources, and then map them onto a given sort of virtual hierarchy within the switch, right? So all of that function of binding resources to a given virtual hierarchy happens through the Fabric Manager. There are FM APIs that are defined, and it's media agnostic in the sense that we use MCTP. So you can get to that Fabric endpoint through different media, right? You could be USB, BMC, SMBus, Ethernet, right? Many different ways of accessing that. In general, you're looking at this for setup and management of that. So I think we've said it need be performant, in which case it cannot be horrendously slow, but you really don't requiring it to be using it at highly performant, because these are tasks that you're using infrequently for memory either allocation or management of that device, right? I think I touched on most aspects of it. We have some examples that we will go through that talk about the Fabric Manager and some aspects of how memory pooling and sharing can work with the FM involved in it, right?
Is there any FM implemented yet, like publicly available, or?
Yeah, I think that is something there is a lot of work that is ongoing, right? In terms of what FM is. I don't know, Vince, you can share about any general public.
There is as part of the Linux community, there is work underway. There's actually a talk tomorrow afternoon from someone at ByteDance that's been spending a lot of time implementing an open source Fabric Manager. Yeah.
Yep. All right, so we'll go through some examples of all of the different device types that we talked about, and then how does that work, right? So in this example, we're showing, you have a CXL 3.0 switch. Just simplistically, in this case, it was a Type 3 device that was, solely all of its resources were allocated to host 2, right? And then the host 2, notifies to the FM that, it doesn't need the memory anymore. So it just says that D4 memory is no longer needed, and, you're relinquishing your resources, right? The Fabric Manager will then, using the FM API, talk to the switch, tells the switch to unbind that D4, right? So in which case it says, you have memory that was connected to host 2 resources mapped in that virtual hierarchy. It says, do a hot remove of that device, of that memory, and send the notification to host 2 that, the memory is offline, right? So there's a lot of work that is ongoing, even with CXL 2.0 in terms of memory online, offline. So use those flows to notify the host that, you've offlined the memory. Then the switch, FM tells the switch that, it wants to bind that D4 resource to a host 1. So it notifies the host 1 to hot add H1, right? So it says hot add this D4 memory, and then H1 enumerates, finds its memory, and then configures accesses to D4. Right? So that's a way to dynamically unbind and then bind that memory to a different host. The same concepts apply now if you have sort of a pooled memory, right? And in this example, host 2 is connected, has memory mapped in D4 and D2. H2 notifies that some D2 memory is no longer needed, right? Says, I had that pooled memory, I want to give up, I don't need those resources anymore. You notify the FM. It tells the switch that, deallocate some blue memory. Now in this case, the FM has to also talk to the device, right? And say, it's going through that device and saying, I'm not using that LD partition anymore, and then it's going to be mapped to some other device, right? And then D2 then notifies H2 saying, I have access to that particular memory, right? And then you can map it. Now you want to allocate that memory to a different host. So the same thing, you inform D2, and then D2 notifies the host that I have memory available, and then the H1 updates his HDM ranges and maps that memory, right? So all of this coordination happens through the device and through the switch, through the FM, and making use of the hot plug flows that are defined.
Isn't that you have to
Okay, so a lot of this was DCD. You can definitely, the mechanism to do that would be DCD, and we'll talk a little bit about that in terms of you can do that today. There are proprietary ways of doing things today, and in the CXL 2.0, there is a lot of work that is ongoing in the industry. And then when we get into DCD, then if you have a DCD implemented, then you would follow the DCD flows. Right? In this case, you would use the DCD flows to say, okay, I'm going to allocate those partitions. A lot of things were also done in 2.0, and there was some work that predates DCD. So we have to see how the ecosystem is going to handle that. Right? But in the long term, DCD is the way to go because it's scalable and then it supports a lot of the things that you would then extend to GFAM and other things, right? So I would say long term, should focus on DCD. Right. Now, host 2 notifies. This is just an example. If same sort of scenarios, but you're direct attached, and in that case, you attach, you notify, to the FM that some D2 memory is no longer needed. And the same thing applies, the FM will talk to D2, right? In this case, make use of the LD CCI and say, this is where it's mapped, and then you can map those resources and notify H2 of the memory that's available, right? And similar examples of mapping that memory in there, right? So overall, right, when you think about a FAM with CXL, you have to do it with FM, right? The Fabric Manager becomes a key piece of that solution. It's really responsible to participate in all of the bind and bind, allocating LD allocations across hosts and managing those, right? We didn't touch on a lot of other aspects that are related to MLD QoS. As you're sharing a particular device or pooling it across multiple hosts, you have to think about some of the QoS settings. So all of those parameters exist for managing QoS. So the FM participates in that. And then the benefits of having a FAM are, right, again, you're using it for better allocation of resources. You need that mechanism. The FAM gets, the Fabric Manager, FAM gets involved in dynamic allocation, deallocation of memory resources. And overall, from a motivation perspective, right, you're looking at TCO savings going on with FAM, right? So those are some of the benefits that you would use with that. Okay, we'll touch on DCD devices, right? So before DCD, changing memory allocation was very disruptive, right? Before that, you could take the devices of today and say I have partitions. You could enable a static configuration, or you could go in and enable a configuration where you can say I want to dynamically allocate, but there wasn't a lot of architecturally defined ways and mechanisms to do that. So a lot of things that you would have to do that were device specific, you can work in at the kernel level to figure out how you're going to do memory allocation and deallocation, right? And it required you to do some amount of HDM decoder reprogramming, right? Because now I changed the range, and you need to be able to quiesce traffic. System reset were likely if you're thinking about in this space, right? And but with DCD, what happens now is you allow the capability for dynamically changing the device memory allocation, right? What it means is that now you have that particular memory provisioned and mapped through HDM decoders, and within that memory you have regions that you can dynamically map to a given host, right? So the HDM decoders are mapped to a full DPA range, so you say, okay, this is how it is mapped. And within that, then you use the DCD command set to say, which allocations are active and which allocations are mapped, right? I think in the next sessions in the programming side of things, Mahesh Nathu will walk through how you can use DCD allocations. He has a good flow that talks about how DCD flows would work once you have this particular mechanism. But when we talk about pooling and sharing, I wanted to sort of introduce this concept, right? So basically what is defined is per host there's a block-based extent list, so that just stays where do you have a device physical address start length, and then you have 8 dynamic DC regions with different properties. So you can talk about that and say, what's the coherency semantics of that region? Is it sharing? What's the block size? So on and so forth. And the fabric manager is the one that comes in and programs these DCD regions, right? And that sort of is the formation of DCD. It's really important as we're talking about, pooling and sharing for the future. These would be some of the things that we want to apply, right? So DCD is defined as part of the 3.0 spec, and we expect this would be very critical as pooling and sharing solutions are deployed. Right, so that was my section on just pooling and sharing. I think I got some time back, so that's good. So yeah, this would be time to just open up for any questions for what we've covered up to this section. Yeah.
I have a question on your multi-head device.
Uh-huh.
So you have multiple hosts sharing the same memory. Do you allow the host mapping to the same physical address, or they have to be isolated?
Yeah, so the question was, I'm just repeating for the benefit of this recording, right? I think the question was if you have multiple multi-headed devices, and your question was, does the physical address has to be mapped to that, right? So let's talk about the LD fam, and then let's talk about the G fam, right? If it's an LD fam, in which case, you have 2 different host images, and I'm assuming that you want to go down to sharing of that memory region, right? So if your question is, I want to share that memory region between the 2 hosts, then what it means is that each host has a host physical address, right? And that same partition now needs to be mapped into 2 different host physical addresses, right? So I have host physical address A, host A physical address, and host B physical address. They're unique from their perspective, right? Each one will get a HDM decoder range, right? So you will program host A's physical address in that HDM decoder that's mapped through that link, and then you have another host, you will map that host physical address in that HDM decoder. But on the back side on the device, you will map that host physical address to the same device physical address, right? That way now you have that same region that is shared between the two regions, right? And then if it's through DCD, then you're mapping it to the same device physical address, but now your properties for DCD would say that this region is shared. So that's how you get that mapping. Now, when we get into GFAM type of devices, there is a different addressing scheme, in which case you're mapping all of the regions in an address space. So in my address space, I know what is my local node, and also I have access to all of the remote nodes, right? So looking at the address space, I know which address space belongs to which particular domain, and if I map request into that domain, then it's getting into accessing a remote sort of a GFAM region, right? So that's how that would be. I don't know if that answered your question.
That answers it, yeah. So
Okay.
would you say like for the GFAM it's better to just use the CXL Fabric since what you just described?
Yeah, for GFAM you would have to use the CXL Fabric because it's the port-based routing. But I think the key question there would be, once you're using GFAM, it also goes into each system how you're going to map the fabric and the GFAM device in your system address space. So it kind of extends into that as well.
Thank you.
Right. Any other questions? Yeah.
Can you give some kind of feeling for the penetration in the marketplace right now of CXL and what you see for the future?
Yeah, the question was, what do we see penetration in the ecosystem? I would say, the crawl, walk, and run, right? A lot of things. So I'll talk from a consortium perspective, right? All of these concepts, it was important to get these defined because there's a lot of interest in terms of enabling these capabilities. My take on it is we're looking at it at a paradigm shift in memory architecture. So all of these concepts are important. A lot of things will start with CXL 1.1, 2.0 to get memory expansion. We got to make sure that it's functional and performant, right? So we're at that point now, right, where there's a lot of deployment. There are solutions out there for memory expansion, right, and those solutions will get deployed. There's a lot of interest and development in getting into the pooling and sharing concepts, right? So the infrastructure for fabric management, as Vince was saying, is getting developed, but it builds on all of these capabilities that you do, right? So I do see that, the early adoption of that would be memory expansion, and then what follows after that would be some of these concepts, right? For bringing something, a technology like this will require us to have a lot of patience and persistence, right? And just being at it, right? Just day in, day out, at just getting all of the capabilities out there. So when I look into the ecosystem, from enabling a memory expansion device, you have everything that you need to do today, right? And the capabilities are there for people to try out and use as prototypes and POC, explore all of the concepts that we've defined, and pretty much you will see that everything from pooling, sharing, the functional proof points are all there, right? Now it gets into, how do you make a business case? How do you get solutions, and how do you drive that? Right? That's the challenge in front of us.
So if I walk onto the show floor tomorrow, how many booths will I find that have CXL products in them? CXL capable?
I haven't done a survey, but I would say it's mind-blowing.
So I think if you look into, just to add to what Mahesh said, if you look into, we did like compliance workshops on behalf of the consortium, very well attended, significant number of devices. Pretty much, if you look into the mainstream CPUs, my company has CXL on our volume CPUs. His does, right? So, it's out there. And then, there are, I haven't counted, but probably at least a dozen plus devices that are out there. So it's you will have a lot of people that should be there at the floor. Right? I mean, supercomputing, when we went there, it was like a huge amount of demos going on with CXL. So yes, it's real.
Yep. Thank you.
Yeah. And in the upcoming months, we expect to see production level devices out there. So. Any other questions?
So this is the year of CXL, is that right?
Oh, yeah.
There will be multiple years.
Last year was year of CXL.
Decade.
What do we
Yeah.
like? Running.
Yeah. Any other questions? All right. We'll end for break 2 minutes early.
And tell them when should they be back?
Yeah, I think.
10:15?
Yeah, 10:15. We'll give a 15-minute break and then start the other 2 sessions. Thank you.
Okay, it's 10:15, so we'll get started. Again, welcome back everyone for the third section of this training. Couple of disclaimers, right? One is that the slides you're about to see, I'm a kind of old-fashioned, right? So I made them by hand. I didn't consult any ChatGPT. So if you have questions, you can ask me directly. Don't ask ChatGPT. You won't get an answer. And the second thing is there's just a lot of work going on the software area today, right? I think Mahesh and Devendra both mentioned about the ecosystem really like CXL, going gangbusters. So just ton of development, ton of innovation going in the software space. You will see some of that in the different flow booths later here in this. So I'm not going to try and cover all of that, but I'm hoping you will get a flavor of a bunch of things that are happening right in the industry over the next few days. So I'll stick to the really high level summary and not get into details. So with that, let's get started. So this is sort of the starting diagram for CXL software. So this shows the CXL hierarchy as seen by the software. Again, this is a simple CXL 2.0 time frame, right? It doesn't include CXL Fabric, but this is where we start. So a few concepts to introduce, right? One, again, I also label them, right, so you can consult them later. So the first concept to understand is the RCD or RCH, right? So RCD stands for restricted CXL device, and the H stands for the host, right? So that's the host and device pair that is as defined in the CXL 1.1 spec. It's restricted, right, because it has a fewer capabilities than what CXL 2.0 spec enabled. For example, right, the RCDs cannot do hot plug, right? There's a bunch of things it cannot do, but it's maintained there for backwards compatibility promise, right? That CXL spec has said will maintain backwards compatibility, right? Provide right, protection, investment protection, right, going forward. So even today's systems or even modern systems, right now the spec allows a backwards compatibility with these older devices and older host. The other term to understand is virtual hierarchy, VH. Essentially what it is, a CXL root port and everything below that, right? Switches, devices, etc. Those we would call CXL VH, virtual hierarchy. A pretty open-ended name, right, for a reason, but that's what we'll see everywhere in CXL spec that's being used to represent this. The next phase is CXL host pages. It's really a software construct that will combine the number of root ports together. So software can sort of discover the CXL hierarchy, walk the hierarchy. Just like PCI Express, the base of the hierarchy is always described through ACPI. It's something that is not really plug and play, or it can be enumerated. But once they're discovered, everything below that can pretty much be discovered through standard enumeration rules, just like PCI, right? So the first level is always ACPI. The root is identified by a specific ACPI device ID that is that's listed here. So the software will look for that ACPI device ID. Once it looks for, sees that, it knows the hierarchy is a CXL hierarchy in relation to PCI compatible. It will walk the tree using the standard rules, right, that the PCI and CXL has defined to find discovered devices. We leverage PCI Express wherever possible. So what we've done is the hierarchy discovery is basically like PCI Express, but to differentiate PCI devices from CXL devices, we decorate the devices with a specific register structure we call CXL DBSEC, vendor-specific extensions. So there's a number of CXL structures defined to describe different attributes of CXL device that are unique to CXL. So software can look at the devices and know it's a CXL device or it's a CXL switch, and then discover these different capabilities and then configure them or enumerate them independently. Right? So we have different capabilities for example, switches. We have many features that are introduced. One of the features I've just come to mind is CXL isolation. So we have registers that defined for that show up in a root port. So software can know, hey, this CXL root port can also support this capability. I can configure it, I can manage it, right, so on and so forth. So that's really in a nutshell how the CXL discovery works.
Right.
Yes.
What's your intent of showing CXL RP versus PCI RP? Is it for enumeration or what's your intent?
Yeah, I think that's really showing backwards compatibility, meaning that a legacy software will discover this and it'll look at PCI Express RP root port. It's very familiar to it, but if it knows CXL, it'll see the other things and can configure CXL. So in theory, legacy software can just look at the tree and then, right, we'll be able to discover C devices as PCI Express and configure them as PCI Express. It probably won't be able to use some of the advanced features CXL provides, but it can enumerate the tree just fine. That's a good question. Anything else? Okay. The other part that was mentioned earlier is where a lot of industries focused on, a lot of excitement is about using CXL for memory expansion. So when you use CXL for memory expansion, you have to understand that CXL systems are by nature heterogeneous systems. Right? What I mean by that is that the CXL devices have different attributes in terms of memory bandwidth that are not going to match what you know for, let's say, DDI attach, right? It's going to a CXL fabric, one interconnect, it's going to go to another device, and you could have DDR, some other media behind that, right? So latency bandwidth is going to be a little bit different. So what we have to really do is make sure software understands the characteristics of the CXL memory device as a separate, right, than the DDR, and when it's doing memory placement, allocation, etc., it must take into account. So what we've done is, again, everywhere we are trying to extend what's out there. So today, the way software discovers heterogeneous memory is using this ACPI concepts called SRAT and HMAT. So SRAT has been around for a long time. It sort of describes how many NUMA nodes system has and the interrelationship, right? Whether a NUMA node or proximity node has memory or only compute. So that's what SRAT says. HMAT is sort of a new introduction, and software is starting to use that. That is much more detailed and allows software to figure out, okay, what's my bandwidth from this compute resource to this memory, for example, right? So if you are allocating memory for, let's say, a GPU usage or a CPU usage, software can say, okay, here's the best memory node I can use to allocate memory for best performance, right? So all of that, and these systems are pretty complex, right? So now systems have lots of compute units, right? There's GPUs, different accelerators, lots of processing units, and lots of memory nodes with CXL, right? So all of that matrix, right, is what HMAT describes, right, in terms of the latency as well as bandwidth. So the challenge that we ran into CXL was that HMAT and SRAT work really great if your system is static, right? At boot time, you know what system has, and BIOS can, right, set up the tables and tell operating systems, here's the characteristics, here's what you look for. CXL breaks everything, right? It's essentially an open ecosystem, right? It adds a hot plug, right, where systems, right, can add, remove capacity dynamically. So what we ended up doing was, but even then, right, the OS still needs information, right? It needs to know what the bandwidth is, what latency is, right, how to allocate, right? But it's a much more dynamic system. So what we came up with is a structure called CDAT, a coherent device attribute table, that each of the CXL component will expose to the software, saying, here's my attributes, right? Here's the latency from my ingress to my memory, right? The switch will say, here's the latency or bandwidth from my upstream port to downstream port. And what we teach software is to look at all the data, look at the entire system construction and the topology, and then construct what it needs to figure out latency from point A to point B in the system, right? So that's really how CXL has become a plug and play, and I think this scheme has worked really well. Good question. Yeah, so HMAT essentially defines it to be the best case latency, best case bandwidth. So it is idle latency, and it is bandwidth that you can, the most best you can get, right? Those are not like great numbers, meaning that you will not see them in real life, but for the most part, software needs to sort of know which is slow, which is fast, right? So, I mean, to that, it serves that purpose. There have been discussions about whether we should also add loaded latency, right? So software can look at a system and say, okay, when system is loaded, right, what to expect? But that's just a lot of work, a lot of things to get right. So we are not gone there, but yeah, this keeps coming up every now and then, whether we should give software something that's like more realistic than these ideal numbers, right? So, any other questions? And of course, if any of you have proposals, ideas as to how to improve these things that are built, right? Yeah, please bring them up in the consortium, and we're always looking for how we can push the ecosystem forward, right? CXL brings in a lot of new things that we have not thought about earlier, so it brings a lot of things like I mentioned, and sometimes bringing fresh ideas allows us to do things more effectively in the new paradigm, right? Versus just propagating the old concepts. Okay. So the other one that is sort of the fun thing that we had to solve with CXL was interleaving. So if you're familiar for standard DDI channels, this is just very common, basic stuff, right? You get, in order to get best bandwidth characteristics, right? We end up interleaving all the memory channels, right? Or maybe multiple of them together. With CXL being used for memory expansion, we needed to find something very similar. except that the CXL system doesn't have to be, is a tree, right? Unlike DDI, which is generally like a just a direct connect, right? CXL tends to be tree. So we came with a scheme that allows it to be interleaved in a hierarchy, right? So if you look at the picture, we have this concept called interleave set, right? An interleave set is identified as a bunch of devices that are connected together. Each set has a base HPA or host physical address. It has a limit, right? And both are multiple of 256 megabytes, right? And then the concept called interleave ways, which means how many devices are part of the interleave set, right? It can be 248. We recently increased that to, I think, 12 and 16 and 3 and 6, right? I think that was, I should have probably corrected the slide. That came in as a ECN after 2.0. The next attribute of the interleave set is the interleave granularity, and that can range from 256 bytes all the way to 4K in as a power of 2. So so that's what is shown here. And for each of the root complex and downstream switchboard, we need to identify what the targets are. Meaning, if I get an access, get an address, right? Where does the root port send it to, right? Does it send it to this port or that port, right? Same thing with the switch, right? If switch is an access and it's interleaved below that, how does switch figure out which of the downstream port this will go to? So that's the target list. So this shows an example, right? So in the picture on the right, shows memory range 16 to 20 terabytes. That is interleaved two-way, right, at 4K at the host page level, which means when the processor gets the access, right, it's going to pick at a 4K granularity whether it goes to the left root port or right root port, right? If it goes to the left root port, it'll land as a switch. The switch has its own decoders. I think Mahesh mentioned the STM decoder concept, which I used to figure out where to route the address. So the switch has its own decoders, and it's going to figure out, okay, it's the same address range, 16 to 20 terabytes, and for me, it's interleaved four-way at 1K granularity. So every 1K address is going to go to a different downstream switch port, and it'll keep repeating that, right, after 4K, right? And at the end, it'll land up in the device, right? So this one doesn't show all the devices, but there should be 8 devices below this, and the device on the leftmost, right, for example, will get 1/8 of the address chunk. And from device perspective, if you do the math, right, it looked like the same address is interleaved 8-way, 2-way at the CPU level and 4-way at the switch level. And this can just go on, right? If you had multiple switches, like 2-level switches, which is probably not very common, this math keeps working that way, right? So that's really the relatively simple scheme that we came up with that allows us to do flexible interleaving. And obviously this, right, this works really well for non-fabric or non-PBI topologies. For fabric, it's a very different address scheme. This scheme doesn't really scale very well when you think about GFAM, but I don't have a picture to show that right now. Any questions on the interleaving?
A comment. Underneath that, multiple DDI channels could also be interleaved, right?
Actually, yeah, that's a really good point, right? So the question was, underneath that is multiple DDI channels that could be there. So CXL, because it abstracts the device in terms of the CXL.mem access, it doesn't really look into how the device is going to handle all these access, right? So CMX is right? Very often, this device on the left side, right, may have, I don't know, 4 DDI channels behind it, and it could be interleaving those access across those 4 to get the best bandwidth, right? But that's not exposed at the CXL level. From the software perspective, it just is the device with some capacity interleaving at 1K. Within the device, it could be interleaving at, I don't know, 128 bytes or even 64 bytes, up to 16 devices, right? Who knows, right? That's really a device implementation choice, and all that will factor into the CDAT thing we mentioned, right? Device has 4 channels, it's going to provide more bandwidth to the host, and it's going to report that to the CDAT structure I just mentioned in the last slide. Actually, that's a really good way. That keeps coming up, right? Again, there's confusion, right? Again and again. Okay, anything else? All right, I'll keep going. So this is another sort of a topic that we spend a lot of time in the consortium, and trying to summarize this in one slide, right? It's kind of tricky. So the problem that we discovered was that Type 3 devices, right, especially ones that have persistent memory, require a lot of management from the software, system software, right? They don't just they don't just work without any help, right? So they need like simple things like needs to be provisioned, needs to be configured. They often need firmware update. Like if you look at these devices, they're pretty complex, right? So traditionally, all the things like memory training that was done by the boot firmware is now done in a device, right? So if you look at just the training code, it's a lot of code, right? So that means a lot of firmware. It needs updates. So we need someone to push the updates to the device, right? And what we didn't want to do was leave this as a problem for the vendors to solve, because we've seen from other industries like NVMe, where we've seen the success of having a standard interface that allows a generic class-based driver to to manage devices. It's worked wonders for them, right? So we decided to do the same approach in CXL, where for memory devices, Type 3 devices specifically, we defined a standard interface by which a standard driver could access device and manage the device and configure it, right? And so the different OSs can just carry a class driver for memory devices and be done with it, right? If they want to do a vendor driver, that's fine, but the class driver will provide enough functionality so the device can be managed. The things like DCD that Mahesh just earlier mentioned, right? Those are also part of the spec, right? So DCD is a standard thing. This driver can manage that. So if you have a device that supports DCD, you can just plug into a system that has this class driver, and there you go, right? You don't need to have any vendor-specific driver, manager driver, certified driver. All those things just go away. So in terms of what we've done is we had defined a few elements, right, to enable this, right? So one is this number of, again, discoverable capabilities that each device can say. First device can say, I'm the device that follows interface, right? There's a specific class code that we define for this. So you can bind a generic driver to that device. Once the driver binds it, it can figure out all its capabilities, a bunch of registers to memory mapped. And then once we get to the memory map, right, we have a number of mailbox commands, right? This was really not, we looked at whether we can just expose everything as registers, but it just became too cumbersome, right? It's a lot of data back and forth that needs to go between device and software. For example, the firmware image has to be downloaded to device, so mailbox seemed to be like a right thing to do for that. So we went with that, and obviously we allow vendor extensions, and those come in handy if you are doing something unique that the spec hasn't caught up with. But expectation that over time, right, a lot of these things will flow back into CXL specs, so they can be managed in a standard way. But the spec does allow vendor extensions. Okay, any questions? Okay, so this is sort of an example of software stack, and this is sort of a tricky slide to draw, because no matter how I draw it, someone is going to say, oh, that doesn't look like my stack. So example, right, so just take it as in the spirit of that. So like I mentioned, right, CXL is going to essentially extends PCIe. So the stack looks very much like PCIe, right? In many places, we've taken PCIe stack and just added a few things on top of it, right, and get going, right? And you can add more and more things and make the system more and more CXL aware. But to get started, you just need very, very minimal stuff to be added to PCIe stack. So if you look at all the way from the bottom, right, so I'm showing two hardware components. One is a PCIe hardware component. Let's just pick NVMe device, for example, right? It's really well known and appropriate for this conference. And the CXL device. In the CXL device, right, I mentioned a CXL memory device. That's a standard interface, right, that defined. So both are at the bottom. At the above layer would be the ACPI or the UEFI layer that describes what these devices are. I mentioned the ACPI construct for the host switch that allows the OS to discover CXL hierarchy. So those will show up at the next level. On top of that, you could take a PCIe bus driver that enumerates PCIe really well today, add some logic to it, and turn it into a PCIe plus CXL bus driver, right? So this driver will now understand CXL, can configure CXL Fabric, CXL interconnect, right? So that's probably an easy way to go from today to the CXL enabled device systems. And on top of the bus driver, you see the NVMe class driver, that's there today, no change, right? So because PCI plus CXL driver is basically like a superset, all the PCI stuff is maintained. You can have a vendor driver that talks to a vendor CXL accelerator device that may be built by vendor A or vendor B. And then we have a CXL memory class driver that I mentioned earlier that is now managing the CXL memory device as a standard interface. The different one unique thing that CXL has that PCI doesn't have is the interaction memory manager. PCI doesn't have coherent memory, so because CXL adds memory, it has to now interrupt with the memory manager that the OSs have, and that's often one of the tricky part, right? Memory managers are very specialized and very, what should I say, difficult, right? Sort of tricky to get right. So this has been some of the struggle that we had is how to interact between the CXL bus driver and memory manager and keep both the parties happy, right? So, but I think a lot of progress is being made, and we're seeing a lot of more and more prototypes, more and more sort of the software out there that's doing these things. Obviously, CXL can be supports hot plug, right? So there's another level of interaction that you need between the CXL hierarchy and the memory manager, where memory can go and come and go, right? And that's something that they were really not very. Today's software doesn't really handle very well, right? Today, memory hot plug is not that common, right? CXL makes it really, really easy to do it, right? And DCD makes it even more easy. So those are some of the things that we are currently working through to kind of make sure the memory management, right, is now able to handle those, right, without giving up all the nice things that people have developed over time in terms of management techniques of memory, right. Any questions?
I have a
Sure.
So a nice block diagram. If you want to draw the fabric manager, like which box it will tap into.
So this is really showing a really simple system. It's not in the fabric system. But if I were to do a fabric manager, will be sitting somewhere outside there, constructing this very system, right? So in a fabric kind of a scenario, all these devices that are shown in the hardware, right? They could be on the fabric, and the fabric manager actually attaching them to a system and saying, okay, right, this device belongs to this system. So it's actually constructing this view, right? And once it constructs this view, then the software on the local node can go and enumerate and do discovery. That's probably one way to think about it. Okay. A few things on the hot plug, right? So CXL protocol it does support hot add, also manage hot remove, and we also had support for surprise hot remove, right, with an asterisk, right? And I'll go into what the asterisk means for surprise hot remove. So manage hot remove is sort of straightforward, right? So software is told that now I'm going to remove this memory device. Please get ready. So please, ask your memory manager very, very nicely, can I take the memory away? If memory manager says okay, then you can support go to the remove process. And this is again a lot of steps to do that because CXL is coherent, so you got to create a bunch of accelerators that are accessing the memory, right? Maybe flush caches to make sure when the memory goes away, you're not like left with some dirty lines, right, in the caches that map to the memory. So a lot of the preparation need to be done by software, but software is told ahead of time, so it can do all of those things, right? In order to prepare. It also has to offline pages, right? Tell applications, hey, this page is going away. Please, right? Please free the page because and I'll give you another page, right, in return. So all those things happens, right, in the background when manage hot remove happens. Hot add is really easy because maybe it's coming in, so it's less of a hassle for the software to handle that. Software sees more memory and it can start allocating to applications. Right? So that's less sort of a tricky kind of flow, right? Surprise remove is what we call goes by the name of CXL acceleration, right? So CXL acceleration was an ECN that was added after 2.0 that allows surprise remove with an asterisk. So it does require support in the root ports in order to handle that. It does require significant software support, and the software recovery after that is sort of the best effort, right? If we do really well in terms of getting the software ready, I think there's a good hope that we can handle it most of the time, but there could still be scenarios when the separator is hard to move, right? If it's done in the wrong time, if there's an application using memory, it could still result in failures. So this is really an exciting area where we want to spend more time trying to figure out how far we can push the envelope, right? Separator is hard to move is fact of life, right? And then we learned it hard way that like, devices, right, the links go down, right, devices get yanked, so we needed a solution for that, and I think we have an architecture solution. How far industry can take this, right, to innovations and different ideas, right, is something that we obviously are very eagerly watching. Clearly, right, I mean, this goes without saying, PCIe has a long lead over us, right, in terms of enabling hot plug, right, and they have a pretty mature model in terms of the hot plug model, all the indicators and everything, right, and different form factors have adopted them, right, so CXL just happily inherit all of that, right, as is and not even bother. A lot of the slots are, I mean, most slots are going to be common PCI and CXL, right? So therefore, right, we have to really follow PCIe in terms of what they do for form factors and some of these things, right? Because from system design perspective, right, there's no unique CXL slot. It's the same, right, as PCIe. Any questions? Okay. Right. So this sort of shows the Type 3 device hot add. And it'll show some of the, I'll talk about some of the points I made earlier about it looks easy, but it can be pretty complicated, right? So I divided it in 3 steps, right? One is the steps that are just like PCIe, that like we know, right? Software understands, right? So the first step is system firmware at boot time has to prepare the system for hot add future. It has to know system can take hot add. So it may have to sort of reserve some address space, right, for the hot add devices to show up. Somewhere along the line, the user will hot add a Type 3 device, right? The PCI hot plug interrupt is generated because we leverage PCI Express, and then the PCI hot plug software will come in and say, hey, I have a device now there. I will assign all of the IO resources to it, just like it would do for PCI hot add. It would assign the base addresses, it would assign memory, IO, all of those things, as it would do for PCI. So this ends the PCI-like portion of it. Now we need to bring in a CXL aware software that can do rest of the steps, right, that are really CXL specific. It'll look at the HTML decoders on the device and say, okay, how much memory do you need? It'll configure the decoder that I mentioned earlier all the way from the root port to the switch to the device. Say, okay, now you know how to decode this address range, right? Here's the address that you've been given. It can configure a CXL DVSec that are right based on which features are enabled. So that's again part of the device initialization. And then it'll use the CDAC table that we mentioned to extract the information from the device, saying, okay, what's your capacity, what's your latency, what's your bandwidth, right? And so that way software can allocate, make intelligent software allocation decisions, right, into some memory. So that's the CXL aware software part. And then it goes into memory manager saying, okay, a standard capacity add steps from the manager would be to, okay, now you have new capacity. The memory manager will process the request saying, okay, I have new capacity, this is the address that I'm getting. Now I'll add it to the pool that's available to applications to allocate from. And then basically we're done at that point, right? So applications can now allocate from the new memory. If they are aware, they can say, okay, I want memory of this characteristic, this bandwidth, this latency, can you give it to me, right? So all those things can happen after that. Again, this is a simplification. DCD makes it a lot easier because there's no physical hot add that's involved in there, and I'll go into some of that in a minute. So dynamic DCD, right? So Mahesh Vag covered some of this, right? So I will probably skip some of the details, but we needed something that's like hot plug is like really a big hammer, right? So we need something that's like lighter weight, more efficient. That allows things like efficient page reallocation from one node to another node, right? So multiple hosts are running, right? And workload dynamically changes, right? We needed like at second granularity, take page away from one node, give it to another node, right? Something that's really quick, right? Not something that takes hours or days, right? Or months, right? For example. So we had defined events that the device can notify the host saying, okay, I have more capacity that I can give you, or I can take capacity away from you, right? There's handshake from the host because the host really has to accept those requests, right? You can't just push memory into the host, right, without its consent, or take it away from the host without consent. The system will crash if you do that. And then allowing the FM, right, the fabric manager, right, to manage the device capacity and say, okay, this host is asking for more memory, I'm going to give it to him. This host is done using its memory, it's like running, has fewer workloads running, it doesn't need that, so I'll take it away from this host and keep in my back pocket in case someone else asks, right? So all that magic is done by this by the FM, right? So we support up to 8 regions in a DCD device. Each can have different characteristics. So some can be like high bandwidth, some can be persistent, some can be volatile. All of those things combinations are allowed. And each region essentially will span what we call the device physical address range in the device, right? It's a DPA range. So it can also expose shared memory region. So again, that was discussed earlier, is that a device can say this region can be shared. So software can set up sharing between 2 hosts in that region. Each host will see a different physical address, but in the end it will result to same physical location or memory ranges in the device, right? So the data can be exchanged between the hosts through that mechanism very efficiently. And there are 2 types of DCs. One is, again, was mentioned, was memory pooling device, or the multi-logical device, or a GFAM device. A GFAM device is extremely flexible, and only way it operates is through DCD. You can allocate only to DCD. The multi-pooling device, you can do other things, but DCD is a preferred mechanism to sort of allocate, deallocate memory and make the system more dynamic, right, in terms of and agile and responsive to the workload needs. And I have a picture that sort of shows that. So this is a simple flow, right? So if you look at this, there's an entity called orchestrator, maybe data center level entity that is looking at all the workloads, saying, okay, I'm going to schedule this workload here, I'm going to move this workload there. All of that is the orchestrator, right? And again, these are terms that are sort of loosely defined. They mean different things for different installations, but so take it with that. The fabric manager we talked about, that's the magic entity that's going to do the allocation. And I'm showing 2 hosts for simplicity. They could be multiple hosts, right? Each host has a generic CXL type 2 driver that we talked about earlier. And you have memory pool device that I'm showing here a simple device, not a GFAM. And it exposes 2 logical devices, right? Both have basically DCD. So let's say the orchestrator decides to schedule some workload W onto H2, right, host number 2, and that workload requires 512 gigs of memory. Now O will see H2 is using all the memory. It doesn't really have any memory left, right, for this new workload, but H1 is not, right? So O will ask FM, right, to say, can you get 512 gig back from LD1? FM will ask LD1 to give memory back. LD will ask its host to say, can you release the memory? The OS on the host 1 will say, yeah, I think I can do that, right? And it'll return to FM all the orchestrator, the task is done, right? So now O knows there's a 512 gig of memory that's available that he can give it to H2. He'll give it to LD2, which is assigned to H2. And there's a tag mechanism that's used to figure out, to reference the memory, right, effectively. I'll skip that for now. And once memory is given to H2, the O can now schedule the workload, the new workload onto H2. H2 has enough memory, and H2 is happy, right? So this is sort of a simple flow. You can do something like this for also sharing if you need to. Any questions? Okay. Other topic that I want to cover is performance management, right? In terms of the CXL device, if you look at it, it's very tightly bound to the host, right? Unlike PCI Express. So what we figured out was that any glitches or anything on that can happen on the CXL device side can greatly affect system performance. And today there's existing infrastructure for managing system performance, measuring system performance, monitoring performance, right? That a lot of the architectures have. Right? There's an infrastructure that Linux has that is pretty well developed and very widely used to monitor performance, right? Provide feedback to applications, help with debug, or right, even just right, even in the system that's deployed, right? So we essentially defined a register interface that software can now use to access performance data from the device and then feed that back into the infrastructure. So it looks at the P1 infrastructure can now look at the data from the CPU and these devices and put it together and see where the bottleneck is, right? What's on, why is my app so slow, right? So those types of things can be done with this. So CXL device has what we call the CXL PMU, Performance Monitoring Unit, that can essentially expose a lot of the data, right? So device can have multiple of these, each can say, okay, I have these many counters, I can support these many events. CXL spec define certain events, and we allow vendors to extend that as needed, right? So again, this is really trying to fit into the existing software infrastructure and not having to ask software, right, ecosystem to build something unique for CXL, right? So that's really where a lot of these decisions were made on. Okay, I'll keep going if there's no question. So CXL error handling, right? So there's two, if you look at the CXL device, right, there's two domains, if you, right, think about it, right, for error management. One is the device, part of the device that's facing the CXL link, right? We call them the protocol, right, aspect. Other one is the back end of the device, which is very not tied to the CXL protocol, but let's say a memory device, this could be a DDI channel that Jim was mentioning, right? So if you divide it into two, the protocol errors are handled and are sent to the host by the device through PCIe-based mechanism, right? We decided to leverage PCIe because it's pretty robust, and again, it can. So what we do is the errors that are happening on the protocol side are reported to PCIe mechanisms using either corrected internal errors or uncorrected internal errors. Right? Those are two types of errors that PCI defines. So we sort of leverage that. It gives us good compatibility with PCI, a really good starting point. Loses some details, but those are filled in by the CXL spec. And on the memory device side, right, we mentioned standard interface, so those are also used to extend to memory event logs, right? So if there's DDI or DRAM errors, right, we define formats for those, so software can say, okay, behind this device I have these many DDI channels, and here's the what's going on with my device, right? So all of those things, the both signaling as well as logging is defined to CXL spec, so that can be managed for a memory device. For let's say third-party devices, you can still have a vendor-specific mechanism, right? That can be handled by a vendor to have if need be. Okay, any questions? Okay, I think that was the end of my material. So if you have questions after the session, I'm probably going to hang around for a while, so please reach out, and thank you for attending.
Jeez, 45 minutes with a bullet. I think I owe someone some money. All right. Good morning, still, I guess, everyone. My name is Vince Hashe. I work for Rambus. My background, I spent a lot of time looking at PCIe fabrics. Fabric topologies, getting away from a strict tree structure is definitely a desirable architecture to move towards in like an enterprise and a data center, a large scale type environment, but there are some limitations in PCIe that limit you to a tree structure. There are some very cool technologies developed for PCIe fabrics, but it's all proprietary. It hasn't been standardized. And so that's a key industry need that CXL has now addressed, and I'm excited to talk about what we've done to enable fabric type topologies, leveraging the PCIe backbone, and now introducing these caching and memory semantics on top of it. We're gonna talk about fabrics. So this is based on CXL 3.0.
And there are some, if you've had a chance to spend some time with the spec, you'll note there are a few places it mentions, certain key aspects of the architecture are coming in a future specification. So we'll talk about them. I'll talk about the needs, and I look forward, when those details get published, I look forward to holding a follow-on training session where we really dig into the details. We'll start with an introduction to the fabrics, how we're going to enable those sorts of architectures, and then we'll visit fabric management again, just to really make sure there's a good understanding of the roles and responsibilities. When you move from memory management, which conventionally a host completely owns its own memory. It's in complete control because it's DRAM sitting in a box right beside the CPU. And now you take those DIMMs and you put them outside in a separate box with some cables in the middle, and there are a bunch of other hosts there. Half of that architecture belongs to that host, but half of it's shared. And so you need to start dividing up the responsibilities to make sure that a host isn't going to do something on the management front that's going to impact other hosts. So we'll talk about all that. So we needed a fabric to be able to enable some of these disaggregated composable systems. So you've got a pool of hosts, a pool of devices, a pool of memory resources. How can you compose those into working systems at runtime as needs arise? Right. This is a movement that's been going on in industry for a long time now. Things are getting broken apart from just self-contained servers into these pooled boxes of resources. This is something that I spent a lot of time working on in storage, and now we're seeing CXL enable this on the memory front. Scale-out systems as well, HPC, deep learning, machine learning, analytics, large systems where a number of nodes are all collaborating together on one larger body of work. There needs to be a lot of communication through the hosts, and yes, there's Ethernet or RDMA available to pass data back and forth, but the bandwidths are high, but the overhead and latency is also high. So getting a more tightly integrated communication between those systems. So basically, we wanted to add capabilities to expand CXL from just a node. There are arguments for adding CXL to a single node just on the bandwidth per I/O pin argument, the cost of DRAM. There are benefits just within the box, but it does allow us to start to scale up to a full rack system, or maybe a number of racks all connected together, all with native CXL, and not needing to go out to Ethernet. Being able to grow to that scale is very desirable. So what we decided was a good trade-off between overhead in the transactions in terms of an addressable ID space versus being able to hit that scale is a 12-bit ID space. So it's not the scale that something like Ethernet would give you, but it gets you up to 4,000 IDs, which is going to hit that small number of racks type scale that we're looking for. And as I mentioned before, there are some serious limitations to just sticking to tree-based topologies. Basically, it kind of just removes the ability to do anything multi-host, because how do you get the trees to align? So we needed a technology to get us out of the tree-based topology architecture. But an important design goal for all of this is that we did not want to compromise node level properties. We didn't want to start throwing in overhead in transaction headers, for example. That would mean that a single host that is not using a fabric, no fabric requirements or technologies involved, suddenly it's bandwidth drops or latency increases or something like that. So that was a design principle that we maintained throughout this development. So here's how we addressed composability. The idea of composability is basically you have your host and your endpoint at different locations in the fabric, and you just kind of select and connect them together. You bind them together. But as Mahesh covered, we're trying to do minimal extensions upon what PCIe established. We want to be able to reuse all of the existing host software that's there for device discovery and the baseline that's used for device management. So instead of exposing all the gory details of the interconnect across the fabric, there's a virtualization layer that's introduced. So if you can see in the center of the slide, there's a physical topology that has a couple of hosts, host 0 and host 1, and a handful of endpoints scattered around. One of them is an MLD, and just a cloud of fabric interconnect. And it's a very messy, jumbled up physical topology. But when a host goes out and enumerates its topology, the role that the switches that are connected to the hosts and the edges, hosts and the endpoints, a role we call edge switch. These edge switches, they virtualize what has happened. So the logical view that's presented to the host when it does a PCIe enumeration is up to 2 layers of standard switches. So host 0 sees its local one, and endpoint 0 is connected directly to that switch because there's no need to virtualize an artificial second layer of switching. And then endpoints 1 and 3 are connected to 2 other switches, but we don't see any of the intermediate fabric links. All of those details are abstracted out, and what's presented is a virtual link that is representative of the routing path throughout the fabric from the host edge switch to the endpoint edge switch or the downstream edge switch. And that's that connection between those 2 layers of switches. So that's actually a virtualized downstream port and a virtualized upstream port that you're seeing in the center of that logical topology. And host 1 is seeing a similar view where endpoint 3 is local on the host edge switch, and then we've got another layer of switching down. So it will only ever be up to 2 layers of standard switching. There's huge benefits. I hope it's obvious the benefits we get from being able to reuse, the decades of PCIe system discovery and enumeration, software development in taking an approach like this. So that's how we address composability. For scale out, the technology that was introduced is, as Mahesh Wag covered, global fabric attached memory. So this is a highly scalable memory pool. So an extreme example is, this could enable over 2,000 hosts accessing a memory pool of over 2,000 memory devices. All at the same time. Practically speaking, you will see a much smaller system than this. Also, that's taking the theoretical limit of those 4,000 IDs. When it actually comes to implementing real systems, the ID consumption depends on your specific interconnect and configuration. There's port counts to consider and switch node size, but basically this is certainly a much larger pool than one host with its DIMMs and an RDMA to talk to other devices. So the way that this is accessible, this pool is accessible by the host is something called the Fabric Address Segment Table, or FAST. So this is a block of address space that the host assigns in his physical address range. And it gets broken up into identically sized segments of a power of 2 size. And each of those segments maps to a memory range within one of these GFDs. So the host goes ahead and reads from that large pool using their HPA, their host physical address, and the GFD does the translation into what that means in the DPA. So the GFD is maintaining an HPA to DPA decoding for each of the hosts that will be accessing it. Okay, so let's talk about how this sort of scale and this addressing scheme is achieved with the transport level changes in 3.0. So in CXL 1.1 and 2.0, we call the routing model employed there, and also in the non-fabric ones, the non-fabric deployments of CXL 3.0, we call it host-based routing, right? Fundamentally because a lot of the transactions are routed by host physical address. So it's a host-centric routing architecture. The problem is when you're looking at a switched environment, if you are routing a switch link based on address, that restricts those links to a single virtual hierarchy because the hosts are choosing their physical address in a vacuum. And so there's the risk of address collisions. So there's just no way for a switch-to-switch link to resolve routing based on address alone, which is why we needed to move to this ID space. But in the legacy HBR transaction packets, address is the only routing information that's defined. So 3.0 introduced a new routing model to enable CXL Fabrics, which is called port-based routing. And the term port is used as opposed to host because you're routing now based on your destination port, not based on a particular host's address range. So this is part of the new flit mode defined in 3.0, the 256 byte flit mode. So you'll see highlighted here on the right are new fields that were added in previously reserved space with some IDs. So there's a destination PBR ID or DPID, and that's carried by all transactions. All transactions in a fabric are going to have a destination PID. And select transactions as needed will also carry with them a source PBR ID or SPID. And so that informs, if you can imagine, for a request, the request requires a destination and a source so that when the target of the request completes the request, it knows who to send the completion to. The completion, however, does not require a source because it'll have a transaction tag. So this is how we allow interswitch links to carry traffic from multiple virtual hierarchies because each host is going to have a unique PID. Each target is going to have a unique PID. So the combination of SPID and DPID is going to allow us to isolate the traffic and route independently. But again, this is only enabled in the 256 byte flit mode in the PBR packing. And I'll show you how links figure out what mode and thereby what transactions they'll be using on the next slide. So at link up, when a link's being negotiated, both ends of the link during alternate protocol negotiation, they exchange information on their capability set. And that's how the links are going to figure out how they're going to bring themselves up. So a part of these symbols that are exchanged, you can see in the full list, they're things like PCIe capable, .io capable, .mem capable, .cache capable, and so those sorts of capability indicators are how a component will detect. So a switch, for example, will detect on the far end of a link whether it's a type 1, type 2, or type 3 device. Can it do .mem? Can it do .cache? Can it do both? They'll exchange what type of flip modes they support. An MLD will advertise whether or not it requires the MLD link mode. And then at bit 18 is where it advertises whether it's PBR FLIT capable. And so this is how the PBR capable links or fabric link, if you want to think about it in those terms, will advertise to the far end. If both sides are PBR capable, they'll negotiate into PBR mode. Otherwise, they'll fall back to HBR mode. So if we think of the previous block diagram where there were a bunch of intermediate switch links, and those edge switches had a combination of endpoint links, host links, and links to the purple cloud of fabric interconnect. So those switch links can figure out whether or not they're linking as an intermediate fabric link, or whether they're linking as an edge to an endpoint or an edge to a host based on the advertisement of this bit on the far end of the link at negotiation. Okay, now we'll talk routing model. I've spoken in general terms that we use ID to route, but the host isn't using IDs. We want to be backwards compatible. The endpoints, or the legacy endpoints, the non-GFAM endpoints, they're not using ID to link. They're just regular type 3, type 1, type 2 endpoints that you could plug directly into the host. So we'll walk through a transaction passing through a fabric to show you where these transitions take place, how traffic passes through a fabric. So I've kind of simplified the representation of the fabric into just a path from a host on the left to the components it's working with on the right. And so we've got 3 different types of target component. So there's a GFD, a device, and that could be anything. That's just, what we mean by device is not a GFD. So this could be a PCIe endpoint, this could be an SLD, this could be an MLD, this could be type 1, type 2, doesn't matter. It's a device, it's a non-fabric device. Or an HBR switch. That could also mean a PCIe switch, but basically not a target device. It's going to do its own decoding and routing. The host, as I said, is HBR. We don't want to impact the host and force the host to be fabric capable. So it's operating as it would were there no fabric there. And we've got the PBR switch there, which is the technical term for a fabric switch, and it's operating as a host edge. It's that host edge's responsibility. I mentioned the virtualization of the topology as one of the roles that it fulfills. The other is it's responsible for converting the host transactions from HBR format into the PBR format that's going to be used inside the fabric for routing. So the host request is sent in HBR format to the host edge switch. The host edge switch converts it to PBR. And then at that point, that conversion on a low-level basis, that means decoding the address, discovering what target endpoint that is, and applying a DPID. So now we've got a PBR format with a DPID and an SPID, because the host edge knows which host that came from, so it can apply the SPID as well. And it's just going to pass that off. If there are any intermediate switches, they'll just route based on DPID. So a PBR switch, one of the requirements for a PBR switch is basically a table whose a 4K table whose index is DPID and output is egress port. Basically, it's routing table. So all those intermediate switches are going to decode the DPID and choose a routing port. If the DPID is a GFD, you'll note from the dotted boundary of the fabric, the GFD is actually inside the fabric. We mark the fabric border as where HBR turns to PBR or vice versa, right? But the GFD is dealing with PBR flit. So that intermediate PBR switch connected to the GFD, it doesn't actually really know that it's sending it to a GFD. It just knows that the DPID is out that port and the GFD is going to take care of the rest of the decoding. So if the decoding that happened at the host edge meant the transaction gets routed to the GFD, then it just gets straight routed to the GFD in PBR flip mode. For all other endpoint types, however, you need a downstream edge switch because you need to now go back into HBR mode. So the downstream edge switch, it also has binding information. What endpoints have been bound to which host virtual hierarchies. And what that informs the downstream edge switch is of the SPID, basically. So it'll receive a request, it knows the DPID, it will also be able to evaluate the SPID to understand what was the source host and how do I reconcile that with the binding information that I've been configured with. Based on that information, it will convert the PBR flit mode transaction back into HBR mode, where it'll pass it to the device. So now the device receives an address targeted transaction. It'll process it, provide a completion, and the whole flow happens in reverse. For an HBR switch, it's basically the same premise. An address routed transaction pops out into the HBR switch, and it's got its own decoding and routing logic, and that can filter down into whatever the switch topology looks like downstream of that switch. Okay. Any questions there? Yes. We'll do the back first. Yeah.
Yeah. So the routing table versus a couple slides earlier, you mentioned about fast.
That's right.
Are they the same thing or
they're different? They're different. Yeah. So.
Can you elaborate what is the difference?
Yeah. Absolutely. Yes. Yeah. So the question was the routing table that I referenced for the intermediate PBR switches and the fast that was mentioned previously in the GFAM, are they the same or are they different? And they're different. The fast is it's the index into the fast is a host physical address, and the output is a DPID. Whereas the routing table in the PBR switches, the input is a DPID and the output is an egress port. So there'll be a bit of, in the host edge switch, there'll be a bit of, likely as a design optimization, there'll be a merging of those capabilities where the input will be address, the DPID will be applied, but the output will be an egress port. But for the intermediate switches, they don't have a fast. The fast is specifically at a host edge port.
Got it.
Yeah. Another question?
What is the typical delay through those switches?
Question is, what is the typical delay through those switches? Well, I'm sure some switch vendors are going to have some booths at the exhibition hall. That's a very interesting question. I would say latency is one of the biggest concerns that I've certainly heard people voice through the development of these systems. A really good PCIe switch, Gen 4, Gen 5, I mean, you're talking anywhere from 75 to 100 nanoseconds one way through the switch. So round trip, that's a big number. And that's based on a certain node size, a certain number of ports, right? The larger the switch becomes, the bigger the silicon, the bigger the crossbar, like it starts to impact latency. So I can't give you a hard answer, but that's definitely an area of an intense focus in the development of these, because there's a big trade-off between increasing the switch size, enabling larger fabrics, but also impacting latency, and what's an acceptable round-trip latency. I will say, though, that for a memory type such as GFAM, the use case would be such that it would be expected to be a bit more of a cooler memory tier. I don't want to say it's cold memory, but it's like you're not going to put your OS image in GFAM, right? This is for like large pools of shared data that can tolerate, whose interaction model can tolerate a larger latency head. Okay, let's spend some time talking about the fabric management architecture now. So as we disaggregate this memory, there are some new challenges in terms of how to manage it all, but that also presents some pretty good opportunities for new levels of capability. So the first thing is, as much as possible, we want to be able to leverage existing DRAM management. You know, there's some memory management software that has existed for a very long time that no one is in a rush to rewrite just to make it CXL specific. So we really want to minimize the software and firmware development requirements. We want to leverage existing concepts that Mahesh has talked about, SRAT, HMAT, we got the CDAT now. We want to be able to reuse SPD and PMIC type management entities for memory management. But we do need to extend these concepts because it's no longer as simple as a DIMM connected directly to a CPU. There was really only one physical architecture for memory in the past. You had the DRAM, the DIMM connector, and the memory channel, right? But now you can put any sort of media type on any sort of form factor and just connect it to a CXL port. And what does that port look like? Is that a connector? Is that a cable? Is it an enclosure? Is the DRAM chip down, or is it DIMMs on the other side of the CXL controller? Like, there's a lot of variables, and maybe over the next 10 years, the industry converges on one specific form factor, and we can just assume that it's going to look like that, but we can't dictate a form factor at this stage. So we need to extend what is reported in terms of topology. The PLDM Type 2 platform data records are used now in CXL for reporting the architecture of the physical architecture, physical topology of the CXL memory module. And we need redfish models to be able to advertise that to higher levels of management software. This really, it's become clear over the years, and I'm sure many of you have seen the announcements that have come out over the years about CXL Consortium working together with JEDEC, working together with DMTF. It's become clear that standardization and really pulling together as a broader industry is a key to being successful in this area. So in the consortium, we rely on DMTF support for development of redfish models, for finding good ways to track CXL, port CXL concepts into DMTS standard-based concepts. So it will really help unify the industry under one model of management.
So what is PLDM?
PLDM? PLDM is it's a platform level data model. Yeah. It's a family of specifications published by the DMTF for various aspects of management. So, for example, Type 5 is a definition for firmware update. Independent of what the device type is, a lot of different types of devices run firmware. And so there's a firmware update standard. Type 2 is a generic way of reporting out sensors and effectors. So that could mean temperature sensors, that could mean voltage sensors, that could mean fan control, things like that. So standardizing generic common management type capabilities. Yeah. So what is a fabric manager? Ultimately, a fabric manager, there will in the future be an open source fabric manager software project that can be reused and deployed. But from the CXL specification definition of a fabric manager, it's not limited to that one project. It's not dictating development requirements for one body of software. The fabric manager is a conceptual term, really. It refers to application-specific logic that is responsible for composing systems, allocating pooled resources, managing platforms, and the sorts of activities like that are required when it's no longer just the host's responsibility for managing the components that are exposed to it. And that can take a lot of different forms. So that can be a BMC inside a rack mount appliance. So the picture I've got here is a JBOM, just a bunch of memory, which is some sort of rack mount. If you can imagine a rack mount appliance that's got a bunch of host ports on the front and a bunch of hot pluggable memory slots. Maybe that's DIMM, maybe that's EDSF, an EDSFF form factor, E3.S, maybe it's a ruler, who knows, right? Maybe it's something that's yet to be defined. But some kind of BMC running in there, doing some management activities, tracking errors, tracking temperatures, and communicating. We've talked about, Mahesh talked about the orchestrator taking some sort of external cues, maybe, about the decisions it needs to make, the processes it needs to kick off. In a smaller, more integrated system, it could just be management software running on the host, making decisions about how to manage a platform. Or if you have a very capable CXL switch with an embedded firmware, maybe you don't need the BMC anymore. Maybe it's just running the CXL switch. But in terms of how it concerns the specification. The components just need to know when an external management entity is accessing them in a fabric management role. That's what we specify. How the components need to respond to a quote FM. The reason we defined it so flexibly is because we need to enable a variety of applications. It would be easy to just get focused on data center or enterprise or HPC and think about these large systems where you do have a big body of software like an orchestrator talking to hundreds of BMCs, helping to deploy workloads and things like that. But this is kind of just generically speaking the future of memory, right? So we need to be able to support industrial or automotive, embedded type use cases. We certainly want to address hyperscale, but we want to leave as much flexibility as possible. And so to enable that, most management capabilities are optional. You don't require an FM just to deploy CXL. But there are certain CXL-defined capabilities that are on the more advanced side that are going to require an FM, right? So composable systems. You can't really dynamically compose a system without an FM. The FM is the entity responsible for assigning the resources to the host. You need somebody to do the binding and unbinding, the allocation of memory and deallocation of memory. Memory pooling as well. When you have a pool of memory, that's no one host's memory. That's a shared resource. So you need a manager of that shared memory. So those are the sorts of responsibilities that fall to the FM when you can't rely on an individual host to take care of them.
Would you please remind us what CCI is again?
Yes, I've got a whole section on it next. So the CCI is the Component Command Interface. I didn't plant that question.
I don't believe that.
So the Component Command Interface, or the CCI, are the target of the management commands. So that's the term we use to refer to that the target of those commands. There are two types. There's a mailbox CCI, which is presented through MMIO space. And then there's an MCTP-based CCI. So that's presented as an MCTP endpoint over whatever physical transport it is, as long as an MCTP binding spec has been defined for it. So it's not a queued interface. For those of you that are familiar with NVMe, it's not like an NVMe admin queue interface. It's one at a time. But that does not mean that lengthy operations are going to back up the interface. There is a concept of a background operation. So firmware update can take seconds, even minutes, depending on the size of your image, to complete. So we don't want all management activities blocked until that operation has completed. So there's a class of operation called background operations where the command that is sent is not go and update the firmware. The command that is sent is start the firmware update. And there's a nuanced distinction there where the completion of the command is, yes, I have started the update. That's running in the background. Now I can service requests until you want to send a command where the command is tell me the status of the firmware update. The guidance that we use within the consortium for when a defined command should be designated as a background operation or as a foreground. We don't call them foreground operations, but the opposite would be foreground. Is about if the operation is going to take if you expect the operation to take 2 seconds or longer to complete, it should be defined by spec as a background operation. That's the other key distinction or keynote to take here, is that the specification defines when an operation is background versus foreground. It's not up to the implementer. Like the read log command is a foreground operation. You should be able to produce your log data. If I do a bad job designing a device and it takes me 5 seconds to spit out the log data, like I don't report the read log as a background operation. I really should just fix my device. But it's the specification that decides what the interaction model is for a command. And a component can support multiple CCIs with varying capabilities. And so this is how you would enable an architecture where, for example, the host sees the endpoint, sees a mailbox, which is a CCI, and when it checks the capabilities of that mailbox, they're pretty limited. They're really just limited to working with the memory. The host is not allowed to do a firmware update. It's not allowed to get internal logging information. It's a limited interface to just what the host needs to do. And then there's a secure BMC interface, and the BMC is the trusted firmware update entity, which is a model that would make sense when the device is pooled, right? So if you have an MLD, you don't want to allow one host to reset that MLD, run a firmware update, wipe the contents. That's a bit of a problem for the other hosts. So there are also deployments where you don't really trust the BMC. The BMC is checking temperatures and errors, and that's all that it's good for. So it's not allowed running firmware update, and it's not pooled. The host is going to do the pooled update. So there's some flexibility in how the component defines its CCIs and what capabilities it presents on each of the CCIs. So the mailbox, as I said, is located in PCIe MMIO space. There are 2 types of mailbox. The primary is designed for use by the generic drivers that Mahesh referenced. It's intended for privileged operations as far as the mailboxes go. You can optionally add a secondary mailbox, which is its own CCI. It maintains its own logging context. That's designed for just pulling logs and event records if you have some diagnostic software that you want to run, but you don't want to interfere with the operation of the driver. The key distinction on the secondary mailbox is that it does not have interrupt support. So there are ways to configure the primary mailbox to, for example, send an MSIX interrupt when there's a new event record, or on the completion of a background operation. The secondary mailbox doesn't support interrupts. It also doesn't support background operations. So the way that a driver would locate the mailbox is first in the PCIe configuration space for the endpoint. There is an extended capability called the register locator DVSEC. So this is a DVSEC that is defined in the CXL specification. It's going to specify the bar number, the register identifier type, and the address. So if the bar identifier is 3, it means it's referring to a CXL memory device register set. And then you'll use the bar number and the address, which is an offset into that bar, which will give you the location of the CXL memory device registers. Now, the memory device registers start off with a device capabilities array. And one of those, in that array, there will be a capability header. The capability ID is either going to be 2 for a primary mailbox or 3 for a secondary mailbox. And then an address, which will be an offset into that same bar, for the location of those mailbox registers. And then you have the mailbox. And so there's a capabilities register where the mailbox advertises its capabilities. There's a control register where things like the trigger bit are set or configuring some options. There's a command register where the opcode for the command that you want to run gets written. There's a mailbox status register that gives you the runtime status of a command that's in the work, or if there are any errors in the mailbox. There is a separate status register for background commands. And then you have your command payload region. So basically you write your command inputs into the payload region, you write your opcode in, you trigger it to run. When it's complete, you go and you read the outputs from that same command payload region. And it's through the mailbox control register where you optionally configure the generation of interrupts on the completion of commands and completion of background operations and things like that. Next, we've got MCTP-based CCI, and basically all of this just gets packetized, right? So the FM is going to discover all MCTP endpoints based on MCTP-based and MCTP spec-defined discovery. And as part of that, those endpoints advertise the message types that they're capable of. And so if it detects that an endpoint is capable of type 7 or type 8, type 7 is for the FM API commands, which is used primarily by switches and MLBs. And type 8 is the general device and memory device commands. They use type 8. So that's how it'll know it's talking to a type 3 device. And as I said before, it's supported over any physical interface for which an MCTP binding spec is defined. And so much of the control and obviously the payload, those are defined in the bottom here, and those just get dropped into the MCTP packet payload. So if you look at this shared fabric, as I said, any of the shared resources, it's not really responsible to have one host controlling it. So the FM, it really needs to take care of the responsibilities that impact multiple host hierarchies. Of course, the biggest and the first management activity as a system is brought up is the fabric needs to be discovered and initialized. So go out, discover the physical topology, and get everything ready to run, and a big portion of that obviously is composition. So binding endpoints. Once you have your inventory of endpoints, your inventory of hosts, you need to start assigning resources to those hosts. When we talked about the virtualization layer that's presented, how all the fabric details are abstracted from the host can't even see the interswitch links between intermediate fabric links. So they're clearly not good candidates for managing them. So errors that take place on those links and any sort of monitoring and management of those links, that falls to the fabric manager. The GFDs, I would argue more so than MLBs, are designed purely as shared resources. So the host's level of management capability on a GFD is very low. It's almost entirely up to the FM to configure the GFD, and things like access controls. It's the FM's responsibility to configure the GFD to allow a particular host access to a particular region of memory, as one example. And then any unbound endpoints. Maybe when a particular type of endpoint is unbound, meaning not assigned to any host, it's just powered off and unused, but it's the FM's responsibility to manage those endpoints. Once they're bound to a host, the host has full visibility and control of them. But until that time, it's up to the FM. The edge link to the host and the link from a downstream edge and a bound endpoint, those are fully visible, fully managed by the hosts because they have been bound and designated into that host virtual hierarchy. So the sorts of things that need to be managed in the Fabric resources, errors in any shared media, scrubbing media, firmware update, things like that for the GFDs and the switches, and as I said, binding and access control. I also wanted to touch on access protection in a Fabric because that's an obvious concern. How do I stop host 0 from accessing endpoint 2, which has been assigned to host 1? And there are a number of layers in which that access protection is in place. So at the host edge, there's obviously whether the switch has been configured to expose that point. So at the switch ingress, at the host edge switch ingress, if a host has not been configured for accessing a particular endpoint, there just shouldn't be any logic configured for routing to that endpoint. But that's not enough. There's also the routing path. The FM needs to explicitly go in and program a routing path. Each link, if you see DPID X, use port Y. If that entry hasn't been programmed, then there's just no way for a switch to route to it. So that offers some protection as well, because only known usable routing paths should be configured through the Fabric. And then for GFDs, they get SPID. They get access control configured in on an SPID perspective. So when they get a transaction, they look at the SPID and they know whether or not they're allowed to process that combination of target address and SPID. Endpoints don't have that same luxury because they don't see the SPID, but we do have a number of other ways to protect those accesses. So I want to talk a little bit about the roadmap, what's coming in future specifications. We've kind of touched a little bit on some of this already. A big body of work that we'll be publishing in an updated release of the spec is the details of the Fabric management. Right? We talked a lot about who does what and what types of roles and responsibilities there are, but we haven't actually defined all the opcodes, all the specifics of PBR switch management and GFD management. So there's a big body of work there to be done. There are also some communication paths that we'll be enabling in the Fabric. We talked about host to GFD, which is memory access, and we talked about connecting hosts to endpoints. And so the communication model there is analogous to what Direct Connect would look like for Type 1, Type 2, Type 3 devices. But there are some new communication paths that we'll be looking at, including host-to-host communication. How do you allow one host to access another host's memory directly, which is a technology that you need a Fabric to enable. Same with device to device, and I'm not talking about just like .uio transactions that a 3.0 HBR switch can just route from device to device. I'm talking about a device in one virtual hierarchy communicating with a device in another virtual hierarchy. So this cross domain traffic, that's a very presents some very interesting possibilities in terms of system capabilities. Okay, so do a quick conclusion, and then we'll do some Q&A. So 3.0 really introduced a lot of new capabilities. We've introduced fabric capabilities and really expanded upon the fabric management architecture that was introduced in 2.0. Expanded up the switching topologies to go beyond one level to multiple levels of switching. The symmetric coherency capabilities, basically the back and validate flows, are really going to help with pooling and sharing type use cases and cases where endpoints are doing peer-to-peer access in memory, peer-to-peer resource sharing, doubling the bandwidth with zero added latency really speeds up the system, and we're still maintaining full backwards compatibility with 2.0, 1.1, and 1.0. A lot of new usage models enabled using the dynamic capacity device framework for enabling memory sharing between hosts and peer devices. Formal definition of multi-headed devices as pooling and sharing components. Through our switch support, expanding the capability for connecting type 1 and type 2 devices. And really expanding the scope and scale of a memory pool through GFAM, enabled through the fabric architecture. So the call to action, CXL 3.0 has been published for a while now. If you haven't grabbed a copy of the specification, I'd encourage you to do so. We're always looking for more bright minds to help us out in defining the future of CXL. So you're all encouraged to join the consortium and participate in the calls. Follow us on Twitter and LinkedIn for ongoing updates on our progress and activities. Okay. Thank you, everyone. So I guess we'll open it up to, we got a few minutes, so any questions spanning anything that was discussed today, or more importantly, anything that wasn't discussed today. Yes, Sanjay.
This one is with higher link rate in PAM4, you said there'll be bitrate is arbor is going lower, so probability of getting the bit errors, which means the more retries, would be more likely. So is there some work done to see practically what are we observing in terms of the retries happening on the wire?
Yeah. So let me take that question. Let me repeat the question. The question was with PAM4 signaling and higher bit error rate, you are more likely to see replays happening. And is there any studies done in terms of what is the real impact and all of that? So yes, there have been very extensive study. In fact, if you look at the presentation, there is a reference to a paper in there. You can go and look into that. As it's a fact of life that once you go for something like a PAM4 signaling, you're going to, of course, have a higher number of bit errors, which means, try to correct some of them through the FEC mechanism, but you're going to have a higher incidence of replays. There are two ways of handling those things. One of them is, the good news is that PCI Express, CXL, all of them have a link level replay. And we have tightened the specifications so that the replay time is going to be sub 100 nanoseconds. So it should be a don't care from that point of view, and you can look into, like I said, the real bandwidth impact of that is less than 0.1%. So should be fairly seamless, but of course there will be more replays because your fundamental bit error rate went up by 6 orders of magnitude. So.
There was another question?
Oh, how do you get a copy of this presentation slide?
Oh, the question is how do you get a copy of this presentation slide? I don't actually know. I'm gonna defer to Elsa.
If you reach out to us, we can send you the presentation slides. I'll also share the slides with FMS organizers, and they can forward those along.
Okay, just to repeat, so if you reach out, Elsa can send you the slide, but then, Brian, do you want to say anything on behalf?
Well, we always put the presentations on our website, and I'm
Okay.
sure we can do it for these presentations as well.
Yeah, so Brian just said that, they're going to put the presentation material on the website so that you could download.
So you guys should all have a link that you can upload your files to. Have you got that?
No, not yet, bro. So we'll take
Okay.
care of that. Elsa will take care of that on our
Okay.
Yeah.
Yeah. And just so everybody knows, there is a section of our website with presentations going back many years. So these can be added to that, just like the other presentations for the next 3 days.
So we wait for next year to get today.
A couple, 3 weeks, something like that.
Couple of weeks.
Yeah.
Normally we get a hard copy before the sections, right?
Soft
On
copy.
Monday section.
Hard copy of your presentation?
Yeah.
Historically.
Oh, well, anyway. soft
Not
copies
this
are
year, I
online.
guess.
Okay.
So what is the difference between the DRAM CXL and versus the flash CXL deployments?
Oh, what is the difference between? So the question is, what is the difference between DRAM CXL and Flash CXL deployments? So a Flash CXL deployment would advertise itself as PMEM. So there's a persistent memory capability framework defined in CXL. And through the CDAP table reported out for a memory device, it will report things like its bandwidth and latency. So for Flash, that's going to be a very different number than compared to DRAM. And when the OS goes in and discovers all of the media available to it, it's going to make memory tiering decisions based on those numbers. So for Flash, it's going to be a very cold memory tier, and it will be treated by the OS accordingly. But in terms of the other fundamentals of how a device shows up, how the addresses are mapped, the transactions that are passed, that's all the same.
Yeah, I mean, just to add to that, right? I think about CXL, it's an agnostic interface, right? So the media that you put behind it could be DDR, DDR4, DDR5, could be Flash, and then it's up to the controller vendors to see how they're going to productize their solutions, right? So as you can see, there are a lot of innovations in this space, right? Like what I was talking about, it opens up for people to innovate. You can front it with DRAM, with Flash behind it, and come up with some very innovative solutions. So it's not one media type. It'll start with typically DDR4, DDR5, but very quickly there are a lot of innovations happening there where it's kind of bringing all of these things towards a solution.
So is it CXL still pretty in its infancy? It's not a mature product development yet? I mean, I don't see 3.0, right? Most of the 2.0 products.
Yeah,
So question was that, is CXL in its infancy? We don't see CXL 3.0 devices, we only see CXL 2.0 devices. CXL 3.0 came out last year. Generally, by the time a spec comes out and products get designed, validated, and you're going to do them for, these are all at the data center level, right? So they have a lot longer of post-silicon validation cycle, it takes a few years for products to show up. So it's unlikely that we're going to have a 3.0 spec come out and products come out at the same time. So. But yeah, people, that's the, we have seen this kind of a lag in other standards also, which is expected.
Thank you.
Good. Oh, we're 2 minutes over. So.
All right.
All right. Thank you, everyone.
Thank you.